Sì. Mezz'ora. Stiamo accorciando il pranzo. Just in the slides. Sì. Intanto, no. So let's slowly take our seat. I'm sorry for the coffee. And these are the first words of the conference. I'm sorry for the coffee being delayed. So we will have after the first talk by Martin, we will have our coffee, which means that everything will be slightly delayed, but it should be fine. Well, welcome to Chile, to everyone. Thanks for being here. It's very nice that all of you made it, almost all of you. We have a very interesting program today, and we will give you some information then during the week. In particular, you saw we have 2 discussion sessions. We have a new version of the program that came online on Friday. This was motivated by the SOC asking to move one session, the session of binary X next to the post-AGB, and that's why there has been a bit of reshuffling. So we have 2 discussion sessions. The organization of the discussion sessions will be made in a way that all the invited speakers will be asked to be kind of a panel. And so we will have a 45 minutes discussion, everyone, and in every session. And what I will ask you is that every day at the end of our talks, you basically send us some information, some question, something, some thoughts, something that came up to your mind. You send it via email to us, and then we will bring this to the invited speakers, okay? Then we will have another session, which is a discussion about the future, and this will be chaired by Franz, so you will get information about this later. There will be a panel there as well. And we will have best poster prize, and you will be asked to vote. Best student talk. So I ask the students to identify themselves when you're giving a talk. I'm a student. And also, please be aware, where is the print? I don't see him. So there is one of the, actually, I realized only at the last moment that the last talk is given by a student. So let's make sure that he is still, well, that he gets his vote, okay? So there will be time until the very last time to vote. And then we will have also 2 other prizes. One is, because this conference was partially financed by ESO and ALMA, so we will have the best talk presenting ALMA results and the best talk presenting VLT results. So watch out for the data that the people are presenting, and we will show then a QR code that you can scan and vote, okay? And I hope that all of you looked at the code of conduct of our conference. We should all treat each other with respect. Should you have any problem during the conference, there will be some contact points. And so there will be me, so you can come to me, but we have also Ake, can you please stand up? And Julianne, okay? If anybody has any problem, whatever, just come to us. And also I would like to identify the people from the LOC. If you can stand up. So we have Luciano, Martina, and again, Ake and Julianne. So if you have anything concerning logistic, please contact us. And I don't know, do you want to say anything else? Yeah.
There is a dedicated Wi-Fi, so if you are interested, you can have the password here, and there's another one over there.
So we have two Wi-Fi. If you have problem with the visitor of CEPAL, we have our own. And I think that's all I wanted to say for the start. And so then we will start with a special moment. And I would ask our team to show some slides. Yes, so we will start by remembering some of our colleagues that passed away. And who is going to speak about Roberto? Yes, so you can just open your microphone there. Yeah. For Imma. I can, yeah.
Okay. So the last years, we had a few of our colleagues that passed away, and so we have a small tribute to those colleagues. And the first one is Roberto Gallino. It's probably not need to say something about him because he is very well known. He is, and I want to commemorate him mainly also because of his work in the community building. He was in fact the father or one of the fathers of the Torino workshops, which in his Torino was the first. He started the series, and I don't know in which year it was, but it's many years ago. Everybody knows his character. He was very, let's say, happy and very. How would I describe him? Let's say enthusiastic is, I think, the word that fits him very well, or fits him very well. And he I think, transmitted this enthusiasm in his close surroundings. And whenever we met, we had very enjoyable discussions. So for this, we commemorate Roberto.
Next slide, please. Okay. And now we take a moment to remember Paola. She passed away a little over a year ago. She was part of the SOC of this conference, actually. And I have her last email sent from May saying that we have all her support in the organization of this conference. And she is also a person very dear to me, because from the very beginning of my career, she was supporting me when I was still a student, and she actually introduced me to AGB and put me in contact with the people in Vienna for my PhD. She was an outstanding scientist, always supportive, generous with her time, and truly an inspiration for many of us. And Michele can say a few more words.
Thank you. There's probably people who have known Paola for a longer time than me, but with Claudia, we agreed I could say a few words. I was a PhD student, and I'm sure many people in the audience have known Paola through her research. She has given a huge contribution in the field of cellular structure and evolution, and in particular, of course, in the study of AGB stars and their impact. Notably, her work in this field found an expression in the years she founded the SARKI project that she designed and led, a research that really improved our understanding of TPAGB stars through an innovative, comprehensive approach at the modeling. But in addition to a researcher, an exceptional one, Paola was known to be a very passionate teacher and mentor, beloved by students. As a full professor at the University of Padova, which was an alma mater, she played a crucial role in reshaping the master's course in astrophysics and cosmology to its modern international current state. So her untimely departure was due to an illness about which she has been very private, and that she chose to live in the intimacy of her family. This sadly forced her to renounce teaching, but could not keep her away from research, which in the last few years led her to develop updated models and methods for modeling radiative opacity for application in stellar physics that are her most recent papers. Paola has been my PhD advisor and scientific mentor, and I know her a lot scientifically, professionally, as well as personally. And besides astrophysics, Paola taught me something important with her actions. Indeed, she has always been ready to support and defend the weak and the represented and underprivileged, which is a strong example to me. Above all, I will remember Paola primarily as a kind person. Thank you.
So it's an honor to remember now Inma Dominguez, who passed sadly a few months ago. So she did her PhD on the explosion mechanism for supernova type 1a with Jordi Cern in Barcelona. So he's my PhD grandfather. She worked on population 3 stars and AGBs. I remember during my PhD reading her works, very excited reading her works with Sandro Chieffi, and I really learned a lot from her, first at the distance, and then when I had the great luck to meet her. She has been very, very important supporting Spanish astrophysics. She has been involved in management, and not only very efficiently, but also in a very kind way, the way that she was. She certainly was, like Roberto and like Paola, a community building at high top responsibility levels, but also in a small level. I thought, in addition to showing her photos, I would show this picture of La Alhambra in Granada, because there was a lot of Granada in Inma and of Inma in Granada. The ones who had the luck to enjoy the unforgettable Torino workshop in Granada in 2006 probably remember this view from the Albaicín, from El Carmen de la Victoria, and the fantastic scientific and people enjoying sessions there. Granada is a city where science developed during the Middle Ages, where cultures met and people from very different ways of looking at things could work together and thrive. And that was, and of course, it's a city where you can enjoy life. There's passion for life and you can feel it. And that was, again, a lot of Inma. So it's been a pleasure to get to know her work and her as a person. And I've been one of the people who have been lucky to get her support. So.
Okay, yeah, I'm Lars Nyman, and I was asked to say a few words about Carl Menton, who passed away at the end of 2024. I knew Carl mainly through the Apex project, but of course, I think all of you probably know who he is or have worked with him sometime in your career. So he passed away very unexpectedly at the end of last year, and for many of us, he was a wonderful friend, colleague, and mentor. He has also been the driving force and inspiration for so many people in the field of astronomy and astrophysics. I mean, he's interested in basically everything, including evolved stars, interstellar medium, Milky Way, galaxies, etc. So he has a long career in astronomy, basically working on the things that interested him most at the time. So there's been 2 conferences in the honor of Carl that's been held this year. The first one was the Apex Ringberg conference in January this year. Of course, nobody had expected him to pass away before, and he was very much involved in the organization. But the conference anyway served as to honor Carl. And then there was a special conference in his honor in Ingelheim in August, which was called From Cosmic Stellar Nurseries to Evolved Stars Using High-Power Telescopes. And this describes Carl very well in all the things that he has been doing. And coming back to Apex, Carl was the driving force behind the start of Apex. And Apex was inaugurated in 2005. It's still operating. Max Planck is now the only partner, and they have money for operations at least until the end of 2028. And Apex, as you may know, it's one of the more advanced and productive sub-millimeter telescopes in the world. So Carl's legacy will continue not only through Apex, but also through all students and postdocs that he has supervised through the year, and it's a lot of them, and I think some of them are here as well. So yeah, so thank you.
Okay, we will now start officially with the program of the conference. For your information, we plan to record the talks, but we will not make them available on social media. If you don't want to have your talk recorded, please speak up before the beginning of your talk, okay? So by default, we are going to record them. So they will be just for us, they will stay for a few weeks, and also especially for the people that are online, if they are from a different time zone, is basically to be friendly to them as well. And I leave to our first chair then.
Thank you, Claudia. My name is Michele Trabucchi from the University of Padova, and I will chair this first session of our meeting. So our first speaker, an invited speaker, is Martin Groenewegen, who is presenting a talk by the title, Why Galaxies Also Care About AGB Star. Thank you.
Yes, good morning. After this important and impressive remembrance of our colleagues, it's a real pleasure and honor to give the first talk of this conference. She may have noticed there is no abstract of my talk. The reason is that Claudia didn't give me a title. She gave me carte blanche. So let's see how this goes. So the title is Why Galaxies Also Care About AGB Stars. And this should be it. So first I made a slide about the AGB conference series out of my personal curiosity. I mean, we are at number 5 right now. And then I decided to touch on 2 topics that are not so much present at this conference, but nevertheless involve AGB stars. Maybe there are posters, I couldn't check that. So if there are, then please let me know afterwards. First, AGB stars in high redshift galaxies, so the early universe. And the other topic, which is, I don't think, represented here, AGB stars as distance indicators. Okay, so we're at AGB 5. Just out of curiosity, how many of the people in the audience have been at all 5 conferences? 1, 2, 5. Oh, 6. Okay. I also put another conference at the bottom, as you see, IEU Symposium 191 in 1998, because that was the first one that was truly dedicated to AGB stars. It was actually called asymptotic giant branch stars. And so out of curiosity, I tried to see, if topics change over all these years. So for every conference, every row will add up to 100%. So these are percentages on the different topics: stellar evolution, nuclear synthesis, circumstellar envelopes, chemistry and mass loss, pulsation, dust formation, and surfaces, distant binarity, and then resolved stellar populations. And in the very last column, the number of participants. So the IEU Symposium in 1998 was a huge success. I mean, 250 participants is really huge by any standard, I would say. And after that, and we are, I don't know, Claudia, how many people are we really in the room? 120 almost. So AGB 1 to 5 are, roughly considered slightly over 100 participants. So that's a healthy number and a stable number. So that's good to see. Actually, I'd expected that, the emphasis on the different topics would have changed over these past almost 20 years, but not so much. Of course, there are typically like 50 talks. So when you see, where is the pointer here? 5% of 50 talks means, 2-3 talks. And, 20, 30% means 10, 15 talks, on a certain topic. What's interesting is that in the very first one, disks and binarity had a fairly large percentage, then AGB 1 and 2 rather low. I don't know if that's a curiosity or not. Because in my feeling, the emphasis on binarity has grown over the past year. So, and it's now quite stable again. Of course, the AGB 4 was the IOE symposium in Vienna, where there was no formal number of participants, but 48 talks and 98 posters. Probably there's some overlap again. Still there would be around 100 and slightly over 100 active participants there in this, what was also a 4-day meeting. So from this curiosity, let's go to the first topic, AGB stars in the high redshift universe. So here we're talking about unresolved stellar populations. And of course, to understand those better, we need a better understanding of resolved stellar populations. And that we will hear about in quite a few talks, actually by Flavia and also by Marta later in the week. And there, of course, we're interested in mass loss rate and dust production rates. And of course, for the high redshift universe, we're typically looking at the low metallicity nearby analogs, like, for example, Sextans A, which you could already done with HST. But of course, with James Webb, you can actually go as far as Zwicky 18, which is at 15 megaparsec or something like that. Although that's pushing it, certainly with MIRI. So I checked on a few papers in the literature I found on AGB stars at high redshift. If there are others, please contact me after the talk. So, and I've chosen to go from a lower redshift to a higher redshift. So first there is this paper in 2023 that discussed well over 100 post-Starbird galaxies in this redshift regime, 0.2, 0.7 with HST. There, I will quote from some of these papers, majority of galaxies in the sample show features indicative of the thermal pulsing AGB, while others are well fit by TP-AGB light models, so lower contribution. And in the figure, they actually show what then, moderate and light, mild, and heavy looks like in terms of spectroscopic features. They also claim in their sample that, tentative trend, galaxies where the AGB contribution is more important are in their higher redshift regime. So note in all these papers, you have these terms light, mild, and heavy. And in this paper, they refer to the papers quoted there, Roussel and Charlot, Noël and Maraston. And this will also appear in other papers. Going to slightly higher redshift, this paper 2025 in Nature Astronomy, a quiescent galaxy at a redshift of 1. So there the age is about 1 gigayear after the Big Bang. And here they show James Webb near-infrared spectroscopy. 2 figures, the observations and then 4 types of models, which are not, they're offset from the observations. So they don't take the comparison literally, they're offsetted for comparison reasons. And in this paper, they actually favor the heavy and mild AGB contribution. On the right-hand side, they disfavor the light and poor AGB contribution. At slightly higher redshift even, 1.9, another post-Starburst galaxy. This is also James Webb data, and they looked at, or they say, we have this CO and CN absorption lines that are tracing TP AGB stars. But here they actually conclude that the contribution is low or mild in this nomenclature. It also, it's already impressive that you can nowadays do this kind of work. Ambranani published a paper earlier this year in ABJ. Now we're already at a Z of 6.7, so that's 800 megayears. Slightly different data. They studied the ultraviolet bump, which is, of course, redshifted to 1 to 2 micron here. And the bump is clearly present. And they, in fact, consider two models or two contribution to producing this UV bump. Synthesis in the circumstellar envelopes of AGB stars and shattering of large grains in the ISM. And their conclusion is that neither process alone can produce the path that will produce this UV bump. And there they hypothesize that, maybe the winds of carbon-rich Wolf-Rayet stars and or type 2 supernovae are likely necessary to produce this UV bump. So clearly already here, the AGB contribution is probably less than at the lower redshift. Of course, not totally unexpected. And then Z equals 12. And here they observe this carbon-3 line, and they model this line and other emission lines. Conclusion, AGB stars can hardly contribute to the carbon enrichment at these early epochs, fair enough. And such a high COV ratio might just be explained by the yield of extremely matter-poor stars, may even be the heritage of the first generation of supernova from POP3. And I think I have one more paper that I could find. No. So conclusions of the papers that I found on this topic. AGB contribution seems to decline with the higher redshift. This is, of course, not a big surprise. Sometimes, at some point in time, the age of the AGB stars simply is too long to match the age of those galaxies. On the other hand, carbon is present and is enriched. So, where does it come from? But up to an Z equal 2, AGB contribution is clearly visible, although this interpretation in poor light, middle, and strong remains, in my opinion, rather qualitative and uncertain. But all these models that were mentioned are rather old. So, as a community, can't we improve here? Question mark. Complete change of topic. AGB stars in the distance scale. So now we're going basically, first of all, to the local group kind of stuff. Of course, we all heard about the tension on the Hubble constant. And I mapped out here the classical path of how do you derive the Hubble constant. Basically from local calibrators, which is illustrated in this figure from Adam Rees' paper. On the very left-hand side, you have your local calibrators, and I will come back to that. Then you go to galaxies where you have Cepheids and supernova, and then you go out into the nearby Hubble flow with supernova. Okay, and then you get a number around 73, 72, 74. And but on the other hand, you have, of course, the value from the CMB, which is 67, 68. So clearly there's this 5, 6, 7 sigma discrepancy, which is basically the Hubble tension. Okay, so it's all anchored on 4 galaxies. Basically the Milky Way, where you use Gaia parallaxes. But these are also not without problems. You have the detached eclipsing binaries in the SMC and LMC. And then you have this galaxy with the mega maser NGC 4258. Of course, there are, lots of, if you would like to call them, secondary calibrators like IRA, Lyra, and type 2 Cepheids. Of course, fainter than classical Cepheids, so limited to the galaxies you can use them. And on the other hand, you have, of course, the tip of the RGB, and further out surface brightness fluctuations and the Tully-Fisher relation. However, over the past years, 2 alternative distance indicators have become more prominent again. One new, called the JAGB method, and renewed interest in the Myra period luminosity relation. And of course, this touches upon our community. And again, how can we be involved and contribute and understand? The history of the JAGB method is quite interesting, I found, because the J stands for has two origins. First, there is this region called J in this classical paper by Nikolaev and Weinberg, which is basically a CMD of the LMC using 2-mass data. And in this region J, as indicated there, it's predominantly populated by carbon stars. This was, in a way, known from spectroscopy, not too much new there. However, there's a companion paper to Nikolaev and Weinberg by Weinberg and Nikolaev, where actually they studied the Myras in this region, and have given the equation there. But as you can see, there is this term which is almost -1. So if you rewrite this equation, which is in their paper, you actually immediately find that J should be roughly constant. And with the distance model as known at the time, it should be absolute magnitude around -6.1. But they didn't make this remark in the paper. And this actually went unknown for, 20 years, if you like. And it's the basis of the first paper on this JAGB method by Mador and Friedman, where they, you can see the number here, come then with -6.22. And this has inspired a number of papers on this topic. You don't have to read it, as this talk will be on Zenodo. You can figure out the details yourself. So there have been a number of papers doing, similar type of work, slightly different analysis. And you see for LMC and SMC, you see this number of -6.2-ish popping up. You also see studies on the Milky Way, one of them reasonably agreeing, but then there was a paper by Ripoche clearly giving a surprisingly fainter number. And there's also what we found, the paper by my student, summer student, Elsa Magnus, and this paper also included Paola Marigo. We found for the Milky Way a quite discrepant number, but in agreement with Ripoche. So, if you summarize this table, also maybe looking at the last column, what do you take, the mean, the median? Do you fit something? But this is still an open question. Okay, maybe it's constant, but what is exactly constant, if it is constant at all? The median, you fit a functional form. So then you take the mode. The other thing is this selection box in the CMD. What is your blue limit on this J minus K color? And this is quite important. And then there is this question of why is the Milky Way different? And it's different in a direction which you do not expect. In fact, you would expect the JAGB stars in the Milky Way to be brighter than in the LMC and SMC. So why isn't it? Let me go in a little bit more detail on this paper that Elsa Magnus wrote. The basis of that was the Leptelter LPV Gaia-based catalog. The reason is that it went down to, it's on LPVs, but it went down to amplitudes as low as 0.1 magnitude. So in fact, it's a very good AGB catalog. And the other thing that was extremely useful for us, our work, is that it actually has a carbon star classifier based on these BPRP spectra. And this is important because this gave us a handle on, for example, what is the influence of this blue limit in the J minus K color. Okay, some technical details. Okay, we correlate with 2-mass, because this is basically still the only all-sky infrared catalog. And then you can down select either your LMC, SMC, and your Milky Way subsamples. Okay, and then it's in a way simple. Select your J minus K range. Select if you like or not. And nowadays, it's also common to select the range in J magnitude. Then you can, of course, apply other selection criteria, especially for the Milky Way. Do you want to limit your reddening, error on parallax, et cetera, et cetera. And then, okay, you can just simply calculate the mean or the median of all the stars in your box, or you can fit this Gaussian or Lorentzian distribution, add a background term, or not, and you can run hundreds of models, which we did. So for the Magellanic Clouds, there were no surprises at all. We found the results as in previous papers. Maybe one interesting side note is that since we're using infrared and Gaia data, we actually had an alternative way of classifying carbon stars using this method that was introduced by Thomas Lepzelter, where you plot these, one is simply the magnitude, and then, well, the color, if you like, which is a subtraction of two Wesenheit indices details. But the bottom line is that actually this classifier agreed very, very well with the classifier based on the BP and RP Gaia spectrum. Okay, and then again, you can do all your modeling, and the result is that, okay, if you take the mean or the peak of the Gaussian, yeah, SMC and LMC will agree within 0.03 magnitudes. Okay, if you like an empirical calibration, this is what it is. And this is the approach that especially Medora and Friedman take in all their papers. However, on the right-hand side, I actually plot the luminosity functions of the LMC, SMC. And there you can clearly see, well, they're not the same, right? They are different. And even if the mean would agree, clearly if you fit the Lorentzian or the Gaussian, the mode of those distributions do not agree. I mean, they agree, but not at the 0.03 magnitude level, but at a, what is it? Maybe I give the numbers later, 0.06 magnitude level. So this is a bit disturbing because, of course, the luminosity function hides what is a stellar population behind it. And of course, star formation rate in LMC and SMC are not the same. So, even if your mean would agree, but are you happy with that if you don't understand why they agree? So for the Milky Way, it becomes quite problematic, as I say. And here we had really the handle or the opportunity to say something about the contaminations by the M stars. And this is important. So I give here for, if your blue limit is 1.2, your M star contamination is, the numbers I give, 30% in the SMC, but also already 34% in the LMC. If you go to 1.5, it's 4 and 1%, so it's probably negligible. But in fact, we found that, thank you, we had to apply this rather red-blue limit, if you like, 1.5 to, for the Milky Way, have this M-star contamination below 10%. And the issues there are that the closest A to B stars, which have the best parallaxes, saturate in 2 mass. And this is a significant effect. And 3D reddening maps, of course, also with Gaia, they're becoming more and more popular and better, but still it's a limitation. And then of course, there is, Gaia parallaxes are not perfect. You have to apply what is often called a parallax 0-point offset. This is not so well understood. So in the end, the Milky Way luminosity function was only based on 100+ stars. Okay, let's go to, I have a couple of minutes, HST and James Webb. Of course, HST and James Webb do not have a classical J-band filter. Okay, so what do you do then? Well, Medora and Friedman and Lee wrote a paper on the HST F110 filter, and they used 20 galaxies which have tip of the RGB distances. So they make plots like in the lower left panel for every of these 20 galaxies in the infrared, but also in other HST colors. What was it, 475 and 814, I think. It's already interesting that the stars, they base their luminosity function on the scatter at bluer colors, quite over the place is a bit exaggerated, but the blue colors are actually outliers. So, okay, maybe there's blending in these blue filters. So what they do then is actually using the tip RGB distances, they put it all on an absolute magnitude scale. and then actually sum up, if you like, all those 20 galaxies. So this is this cumulative composite CMD on the right-hand side. And so based on 450 AGB stars in these 20 galaxies, they actually give a mode with this number. But again, there's no luminosity function as such shown, and also no metallicity effect discussed. James Webb becomes interesting, and probably this is the way forward. So there you have this 115 filter, and you use another color to make a CMD. So in this paper, they use this method actually in 7 supernova host galaxies. And so here you have to only choose, you have no option. You have to use NGC 4258 to anchor all this. And I give you some numbers below the figure. And even based on those 7 galaxies, you can actually derive a Hubble constant. And, you know, maybe I'm a bit sarcastic because this is a Friedman and Medor paper. They find a lower value of the Hubble constant. Because there was another paper by Adam Rees and his group using the 150 filter in 6 different supernova 1A ghost galaxies, again tied to 4258. And magically, you can derive a Hubble constant, and it's 73. So this becomes, well, what's the right word? Annoying in a way, disturbing, but this is how it is at the moment. So JGB conclusions, which means I have to skip the Myras, I guess. Luminosity functions are not, in the LMC, SMC, are simply not symmetric. They are different, and this must be due to stellar populations. James Webb is probably the way forward, but you know, it cannot be based on the 4 anchors because James Webb will not observe stars in the LMC, SMC, at least not for the current moment. Maybe at some point there will be data in the archive, which means no Myras. There is actually one slide then. There's a lot of work done by Caroline Wang. And in fact, there was a book published on the Hubble constant tension, and there's a chapter on the Myras, and other chapters as well are, in fact, available in the archive. So there's data on 4 objects, the LMC, again, the anchor galaxy, and 2 supernova 1 hosts. What is interesting here, you actually now want oxygen-rich stars. You want to get rid of the carbon-rich stars, basically, because of minimize the effect of dust. And again, based on those 2 galaxies, you can derive a Hubble constant, of course, with a large error, but again, it's 72. Really, final slide. So James Webb is a game changer. High redshift universe, carbon-rich dust is clearly present. What is the origin? At lower redshift, slightly lower redshift, AGB stars are present, but we need to improve the models. JGB, I think it's very powerful because, of course, you need single shot, like the tip of the RGB, contrary to Cepheids. But we need more and more understanding. And for the Myras, I think it's equally interesting. But of course, with this, you always need multi-epoch data. So that's, for James Webb, will always remain an issue. Thank you for your patience.
Sorry to interrupt you in the middle of what I find the most interesting topic.
Mara, sorry, Michele.
Thank you very much. So we have a few minutes for questions. I would like to encourage you to state your name and home institute before asking, for the benefit of the younger people. Most of us already know each other, but okay. So any question from the audience or online also? Please.
Hello, this is Liz Tarantino from the Space Telescope Science Institute. Thanks for that great talk, Martin. I have a question on the high redshift portion of your talk in the beginning. Do you have any idea as to why the post-starburst galaxies tend to be the galaxies at these intermediate redshifts that show the strongest AGB star signals? Like why is it those types of galaxies rather
I
than?
presume it's, it has the right age where you can reach AGB during, the lifetime of these galaxies.
Awesome, thank you.
Thank you. Any other questions? Yeah, hi, Theo Kuri from Chalmers in Sweden. Just following up on that, when a star is classified as post-starburst, how long ago was the starburst happening? Is that something you know, or?
Probably it's in those papers. I think I did quote the ages of the galaxies, but I don't remember then how long post-starburst it was.
Because it would be interesting to compare with the very high redshift part to see if how far you expect the AGB population to show up. I guess we have time for one last question.
Yeah. If there's time, tell us more about Shazreen Mohammed, based at UVA, University of Virginia, also South Africa. So if you have time, could you tell us about the Myras?
I could, but then I need the slides back, please. Okay, yeah. So the two slides I had, well, first of all, the introduction, which I'm sure Michele will also give. Of course, you have these sequences that were really, popped out when we had Peter Woodstock in 1990, which was the first with mature data, and then, worked on by many, including then the Ogle collaboration. This I roughly mentioned, but let me give a little bit more detail. So on the LMC, what Caroline Wang did was take the Ogle 3 sample of oxygen-rich Myras. You combine that with the 2-mass JHK. You actually then transform it to HST using this equation that was based on the spectra of carbon and oxygen-rich stars. And then you can derive a PL relation, which is quoted there, in this filter. So what she does then in the other subsequent papers for the other galaxies, you keep the slope. The slope is adopted from what you find from the LMC, as I said there, in fact. And the other thing that I want to stress again here, you actually really want oxygen-rich Myras. So minimize carbon-rich Myras, minimize the effect of dust. So there are typically also period cuts. I think again, for all the details, you can read upon this later. So there's typically period cuts to eliminate carbon-rich Myras. And of course, you have an amplitude cut to not include too many semi-regulars and really keep Myras. And as you can see in some galaxies, she also took a color cut, again, to probably minimize the effect of dust, because then if you work in one filter in the K-band, say, or the equivalent, if you have dust, your K-band magnitude is not stellar, but it will include the effects of the Sturkov-Zeller envelopes. So then you see the 3 galaxies and the number of epochs and the number of Myras. So number of epochs is, given the baseline, good to actually find the Myras. And I give there 2 examples of then the PL relation they find with a fixed slope. Of course, for example, in the example on the right, you could even leave the slope as part of the fit, which they chose not to. Yeah, that's it. Thank you.
So thanks again, our speaker. And also thank you for your questions. So I guess we have a coffee break now, and we will reconvene in half an hour. Is that right? So at 11,
Wait.
wait.
It's 15. No, sorry. Yeah, let's do 15. If you can make it to 15, but
15 minuti di break.
no, half an hour.
Facciamo 20 minuti.
Half an hour. Yeah, mezz'ora.
Mezz'ora. Okay, let's reconvene in a little less than half an hour. Thank you. Please, everybody take their seat. Okay, please take your seat. We should start. Okay, so we're ready to start. Our next speaker is Amanda Caracas, who's gonna talk about the evolution and nucleosynthesis of AGB star. Would you please be so kind as keep the microphone close to? Yeah, thank you very much.
Right, hello, good morning. Yeah, I'm going to talk about evolution and nucleosynthesis just of AGB stars. I was going to include a little on post-AGB, but there's a whole session on Friday, so I will leave the post-AGB to the experts, and I will maybe just mention their usefulness in terms of constraining the evolution and nucleosynthesis of the AGB phase. Okay, all right. So this is my outline, brief introduction. I'll tell you about AGB stars if you don't already know. A little bit about the slow neutron capture process and the intermediate neutron capture process, but I will really leave also that to some other people who talk today or talk later in this week. Little few puzzles. These are very personal, just things of interest to me, and then some future opportunities and a summary. Okay. All right, very brief introduction. So most evolved stars in galaxies are low and intermediate mass. Most are on the first giant branch, but there are those very important stars that we know on the asymptotic giant branch, and that's why we are here. These stars are element factories and dust factories in galaxies. So what do I mean by that? If we look at the chemical evolution, for example, of the solar neighborhood, we see that some elements, if we carbon, nitrogen, fluorine, which is not shown on the image on the left-hand side, which shows iron to hydrogen versus the elements, where all those dotted points are observations, and then we have the theoretical model lines throughout those dotted points. And we see carbon and nitrogen have a strong contribution from low and intermediate mass stars, AGB stars. We also know that half of the heavy elements are made via the slow neutron capture process, the S process, and the main site of the S process in nature are, of course, low and intermediate mass AGB stars. And a key element that demonstrates this is strontium, shown on the right, where we have strontium versus iron versus, iron to hydrogen versus strontium, again, observed points, and the model line, where the S process is really needed to go through the solar amount of strontium. A little bit about dust. There'll be a lot about this week. I can try and, there we go, oh, wrong way, this direction. I am going back in the wrong direction. How do I go forward? There we go. All right, a little bit about dust. There will be more talks about this, so I don't really want to spend too much time. Just to note that AGB stars are, of course, dust factories. But I think one of the evidences that I think I like to highlight is the pre-solar grain record. These are bits of stardust that we find in ancient meteorites, such as carbonaceous chondrites, and silicon carbide is a key example. And of course, we see silicon carbide features in the spectra of AGB stars, real stars. And so we think that the majority of the stars, again, this is up to see whether I can make sure not, okay, maybe some more than 90% of these silicon carbide grains where we see This is showing the C12, C13 versus nitrogen 14-15 ratios. More than 90% we think are formed in the outflows of these dying low mass stars. And we'll again hear more talks about that, so I won't talk too much more about pre-solar grains. Okay, moving forward to evolution. So where are AGB stars on the HR diagram? Most of us know this. So this is a nice diagram that Falk made more than 10 years ago now, 20 years ago now, showing the, so this is HR diagram, of course, log surface temperature versus log luminosity. And we see that, of course, the AGB stars are found, they're very bright stars, and they're in the red part of the HR diagram. They only live on the thermally pulsing phase for a few million years, but of course that's what where we try and find them to do all sorts of interesting science. And these times just show the respective times that these stars spend in this phase. And this is a typical example of an AGB star, 2 solar mass. Okay. What do they look like from a structural point of view? Well, this is again, if you've seen one of my talks before, you've probably seen the image on the left-hand side. It's just a schematic showing essentially the size of the hydrogen-exhausted core, which is the yellow part of this diagram, relative to the size of the hydrogen envelope. And I like to point out that if so let's say this is a 3 solar mass star, that core might be, say, 0.6, 0.7 solar masses, and the envelope is the rest. To give you an idea, the radial scale, if the core is about the size of a marble, to go to those outer layers, we go maybe a few hundred meters away. So they're very centrally condensed, very chemically stratified objects. Of course, they're driven by helium shell instabilities, and I'll show an example from a theoretical model. And we also have rapid episodic mass loss, and we'll hear a lot about that this week as well. And I put some key lifetimes. This is the total stellar lifetimes. So I think what the interesting thing about this mass range is that unlike massive stars that all live essentially instantaneously by the life of a galaxy, these low and intermediate mass stars, they span everything from 30 million years, tiny, short life, up to billions of years. So this is where the lifetime of stars change dramatically. All right, schematic so the schematic nucleosynthesis and evolution, this shows essentially a Kippenhahn diagram, if you like, where we have time on the x-axis versus mass. So we're moving from the bottom part is the interior of the star, moving upwards, and we have the burning shells. So that we have the helium shell, it produces a convective inner region between the shells, between the hydrogen shell and helium shell. That convection homogenizes that region, that leads to nucleosynthesis, such as carbon-12, but also secondary products, such as fluorine, neon-22, magnesium isotopes. And then we also have, this is the location where the heavy elements are made. We have those helium shell flashes may drive this convective dredge up, third dredge up as we call it, and this may happen repeatedly. Okay, moving on. So this shows a theoretical example of helium shell flashes in a typical star maybe we find in our galaxy. So 2 solar mass, solar luminosity, 2 solar mass, solar metallicity. And we see that the time versus luminosity, and we see that those black lines are the helium shell instabilities, where we can reach up to 100 million solar luminosities in that helium shell. That doesn't reach the stellar surface, but that essentially works to expand the star, and that can lead to convective mixing, third dredge up. What does that third dredge up look like? Oh, in fact, the red lines show the radiated luminosity. So you see the difference. It only changes it by a factor of a few. Okay. So if we look at the helium shell instabilities compared to what happens in the core region, so on the right-hand side, so I've got the helium shell instability shown on the left-hand side as a function of time. And again, now I've just reversed the colours. So red is the helium shell luminosity and black is the radiated luminosity. Right-hand side, we can see the structure of the star. So we see the CO core grows with each thermal instability. The helium intershell becomes thinner with mass in time. And then we also see that the hydrogen, we see the location of the inner edge of the hydrogen core, the hydrogen-exhausted core, and we see evidence of third dredge ups, and there are about 5 we can see. Each of those will mix some primary carbon-12 from the helium shell into the surface, and this leads to the change from an M-type AGB star to eventually perhaps a carbon-rich star where there's more carbon than oxygen atoms at the surface. Okay. So that's for low mass stars. That's what we think happens canonically. But if we think about intermediate mass stars, we have, they can also have helium shell instabilities, maybe third dredge up, but then they also have second dredge up, which takes place during that early part of the AGB before thermal instabilities set in. And also hot bottom burning. This is where the base of the convective envelope gets hot enough for proton capture nucleosynthesis, hot bottom burning. So I've just shown an example from 6 solar mass solar metallicity, and we can see as a function of time the temperature at the base of the convective envelope. And we see that even though it's getting up to 80 million degrees, because of the low density in that envelope, we really need temperatures of 40 million or higher really for C and O cycling. And we see that at the surface C to O ratio shown on the right-hand side, where we start at, say, the solar ratio that goes down from first, second dredge up to about 0.3, and then we see an evolution caused by the combination of hot bottom burning and third dredge up in this model. Okay, all right, that's what we predict canonically. So just a summary of those predictions shown for some slightly lower metallicity theoretical models. And I've just summarised. So roughly 1.5 to 4 solar mass stars become carbon rich and S process rich. Also, we see increases in fluorine in their surfaces. Stars less than about 1.5, this should be approximate here, they don't have third dredge up, so they remain oxygen rich. They only have first dredge up and maybe some other extra mixing on the first giant branch I won't talk about as their change in surface composition. And then the stars more than about 4 have this hot bottom burning as well. Okay, this is what we predict canonically. I'll talk about some puzzles related to this a bit later. Recent years, we've seen some extensions of the parameter space. One example is to very metal-rich AGB stars. So there have been work from a couple of groups on this, including my own, but also Paola Marigo's group. She also extended to high metallicities. So if we move to high metallicity, so this shows the metallicity on the x-axis. It's a bit of a grid of what we predict from the theoretical models. We have metallicity on the x-axis, initial mass on the y-axis. And if it's a kind of orangey colour, the stars don't even make it to the thermally pulsing phase. If they're light blue, they do, but they have no third dredge up. And if the hashed lines we see at the left top have any third dredge up at all. Notice the initial masses of these stars are 3 solar masses or higher. So that means that as we move to very metal-rich AGB stars, we have very little third dredge up. That means that we're essentially seeing an end of the S process. Once you move to very metal-rich stars, no S process, no fresh carbon, no primary carbon will be mixed. They still have hot bottom burning, but now this is just cycling secondary products. We also found that the minimum mass for carbon ignition is lower as we move to very metal-rich stars. So that means that presumably in the most metal-rich AGB populations, we could have a lowering of the minimum mass for core collapse supernovae. Okay. There have been some recent works also looking at very metal poor and metal free AGB stars. So Pilar may talk about this later in the week. But we also have work by Paolo Ventura and Arthur Choplin, and also there's a recent paper by Rempel as well. I'm highlighting, though, a paper by Lawler and McDonald, who worked on some metal-free AGB models recently, and they looked at the initial final white dwarf mass relation essentially for metal-free stars, only up to about 3 solar masses initially. So we see their metal-rich, their metal-free initial final mass relation shown by those stars, those red stars, compared to their solar metallicity. And obviously, as we go to metal-free, we have the stars are burning hotter and they're burning at higher luminosities, so the core masses are higher as well as you move to low metallicities, very low metallicities, metal-free. Okay, a little bit about the S process. So this is the production of elements heavier than iron through neutron captures. The S process operates at relatively low neutron density, so we stay what's called close to the valley of beta stability. So we tend to make elements such as strontium, zirconium, barium, lanthanum, lead, are typical S process elements. I will mention the I process, but Lionel will talk about that, so I won't talk about that too much. But the S and I, they both are powered by, we have to make free neutrons for neutron captures to occur. That takes place through the carbon-13 alpha N reaction for the most part in these low mass carbon-rich AGB models. That happens in the helium-burning shell. I won't talk too much about the details of this, I just don't have time in this talk, but if you're interested, ask me or ask others who work on the S process. Okay, so which stars make the S process? Well, the AGB stars we love and care about. We see a lot of evidence for this. If we look at the surface compositions of AGB stars, and we'll hear about that later even later this afternoon. Typically, we see S to iron. This is some S process element, maybe barium. To iron, that's a plus 1, so it's order of magnitude increase. And this is confirmed through observations of things like AGB and post-AGB stars. Post-AGB stars have shown some of the clearest signatures of this. So a recent work is by someone from Devika's group, Meghna Menon's paper, where she found a star with a very high carbon to oxygen ratio of 16. So we've predicted this for a long time, but never seen one. She found one. And it has also very high, if we look at the S process elements in this star, so we have proton number on the x-axis versus abundant ratio, and we see, and I put a line for greater than 200 times the solar ratio, and that's what we see in this star, which is just amazing. Okay. If we want to do galactic chemical evolution, we need the yield from we need S process yields from populations of AGB stars. And in recent years, we've seen this being made by my group and others, including Sergio Cristello's group. So these are really useful. And we see this is an example, initial mass versus yield for, say, barium, for a sample of AGB stars. But there are quite a few uncertainties. What is the minimum mass really for making carbon and barium? I've set it at 1.5, but that's a bit arbitrary. So what really is it? Can we constrain this better through observations? And how does a binary companion change the stellar yields? Okay. I don't want to talk too much about the intermediate neutron capture process, because Lionel will cover this. This is really an extension of the S process to higher neutron densities. It takes place under the similar conditions, but now driven by proton ingestion into the helium-burning shell. But this is still carbon-13 alpha N that drives it. There's been a lot of work by a few groups on this, but I think some of the most interesting work I've seen recently has come from Arthur Choplin. And I thought this paper recent from this year showing that the I process can reach actinides and short-lived radioactivity. Actinides, of course, are some of the heaviest isotopes that we see in nature. And we see this on the right-hand side where we see a chart of the nuclides, and we see the path of that I process moving up to some of those really heavy isotopes. Okay. All right, a few puzzles, which are interesting to me. I think one of the uncertainties, and this has not gone away, I'm pretty sure the first talk I gave probably at one of these conferences talked about uncertainties related to the third dredge up, and I'm still coming back to this. I think it's important to know if models are providing an accurate description of mixing in real AGB stars, because the third dredge up, it really determines how much helium-rich matter is being mixed into the envelope, and this really drives, this is essentially what is driving chemical evolution from these stars in galaxies. So do current models predict enough third dredge up or maybe too much? And how does this vary as a function of mass and stellar metallicity? So one question we can start with, do the models predict the right mass and luminosity ranges for carbon stars? This is something which has been worked on, but I think we still go back to, the answer is no. So this is an image showing bolometric luminosity, so taking the carbon star luminosity function in our galaxy from Carlos Abia's work. For a long time, we couldn't use the stars in our galaxy, but Gaia has changed it. We can use them now. We think we have a decent understanding of their luminosities, notwithstanding, I know, the uncertainties with Gaia in AGB stars. And if we compare these two observations, so we compare the carbon star luminosity function to theoretical models, say take my models, but really could take, I think, most of the detailed stellar models out there, and you find a thin line shown on that diagram. So no, we predict the model should be too luminous. There's ways of fixing this, of course, and this is something that was done by a PhD student working with me at Monash University. She was making synthetic populations of AGB stars, so not single models, but populations. And so there she could change the minimum mass for making a carbon star. She could change the minimum mass for where third dredge up occurred in the models. She had to lower this to about 0.5 in terms of core mass, and she had to lower the initial mass to about 1.2 for making a carbon-rich AGB star. This is considerably lower than what we find in, say, the detail models, and it can be quite challenging from a detail modelling point of view. But this is, I don't think, new, but I think it still reinforces that the problem has just not gone away, I think, which I think is interesting. There are other observations we can use to constrain the third dredge up that I think really just reinforce, I think, some of the results that Zara found in her work. So we can use the initial final mass relation to constrain the efficiency. This is something that Paola Marigo did in 2022. So we see that if we look at see the initial final mass relation on the left-hand side from using models from a few groups and compared to observations. And then on the right-hand side, we see, if I just focus on the bottom plot on the right-hand side, we see lambda, the efficiency as a function of the core mass. And I think this shows on the left-hand side that on the right-hand side, I'm getting confused. I'm very jet lagged, I have to say. So if I'm talking nonsense, anyways, I'm sorry, I do apologise. It's 10-hour time zone difference is not easy. But I think we see on the right-hand side, that a core mass around 0.5, 0.6, that we see that we do need these stars to be experiencing quite efficient third dredge up already. And in my models, I would find the minimum mass to be about 0.6 from a core mass point of view. So we see that in these models, we have to shift it to lower core mass. And also by the time you get to a core mass of 0.6, that lambda is really efficient. It's 0.7. And that stays efficient till core mass of about 0.9 and then drops off. So clearly we can see that if we use these observations, we can constrain this. And I think one thing, if I now focus on the intermediate mass range, this tells us that third dredge up in these intermediate mass stars should not be that efficient. But there are observations that are confounding here because there are S-process rich, very bright, oxygen-rich AGB stars. They exist in the Magellanic Clouds and they also exist in our own galaxy. But maybe are these just the low mass end of the hot bottom burning? So maybe these are the stars of 0.9 core mass, not 1 solar mass core mass. Maybe. There are also very bright, dusty carbon stars that we don't talk about that much anymore, but there was this paper by Van Loon from maybe 98, not 99, could be a typo. He found these really bright carbon-rich stars. And they clearly have had third dredge up, maybe after hot bottom burning has occurred. So it happens maybe in some of these stars, but maybe again, we're just seeing that low mass end of that hot bottom burning tail. And there are also, and just to go back to the low mass stars, there are also those stars, there's that star that Devika Kamath found in 2017. It's a low mass star of about 2 solar mass that should have third dredge up by its core mass, but it doesn't. So what happened? Why did it not have any, why did it not have any third dredge up? It's like it just failed to have third dredge up. So but we expect all two solar mass stars of that fairly low metallicity, this was in the Magellanic Clouds, should have third dredge up. So why did it not? Can third dredge up perhaps be stochastic in some models? Or in some, sorry, not models, in real stars? Or maybe it depends on some physics we haven't really considered yet. A little bit about extra mixing. This is some non-canonical slow process that can maybe work in AGB envelopes. Again, the observations are telling us both can happen because there are real AGB stars that seem to show evidence of this deep mixing of whatever it is, so similar to hot bottom burning, but in lower masses. So this is results from a paper by Thomas Lebzelter from 2008, old now, but in these stars we saw evidence of extra mixing, that is a lowering of carbon-12, carbon-13. But there are similar clusters that don't show it. Similar metallicities, similar turn-off masses that don't show it in their AGB populations. And also work by Carlos Abia from 2017, looking at oxygen isotope ratios, also found something confounding, that the oxygen isotope ratios, for the most part, do not seem to show evidence for it. So maybe, or maybe not. We also do see there are still ways, we're still looking for ways of including carbon-13 pockets in AGB models. Most people use some sort of convective boundary mixing in order to include it. But there are issues, and I'll point you to a paper by Wagstaff 2020 for details. Gravity waves have also been suggested to enhance lithium production in models of hot bottom burning. I only looked in that paper briefly. It's a recent paper, but this is also, I think, worthy of consideration. Gravity waves have been suggested as as an extra mixing phenomenon for a while now. And there's also proton ingestion in maybe solar metallicity stars that also can lead to extra mixing-like phenomena. And this is, again, work by Arthur Choplin. And maybe this is where J-type AGB stars come from, maybe. And we also see this in, again, the pre-solar grain record, where we have these AB grains. They look like J-type stars, but maybe they are proton ingestion. Just a little bit about also magnetic mixing. We may hear about this from Diego Vescovi's talk, so I don't want to talk too much. I think the main thing is that these magnetohydrodynamical mixing as a way to make carbon-13 pockets maybe they just show different behaviour to other models. That's probably, I'll just leave it there. If you're interested, I think Maria's review paper on the ESO process discussed this in more detail from 2023. Okay. Post-AGB stars are in themselves a puzzle. So this is the observations compared to models. And even though the match is reasonable, we don't really see somehow especially some of these heavy elements don't match. Oh, and also there is the other star in the SMC that showed a really heavy S process. There should be theta O of 1.9, but anyway, slight typo. But this star has really high S process, but it also has really high oxygen abundance. We don't normally predict that. And that star likely made its own oxygen as well, which we don't see in the star that Meghna found. So again, we're seeing, I think the main thing is just a real diversity in their surface compositions. Almost my final slide, I promise. This is the last slide on results. We have been looking at the effect on binaries from a stellar population point of view. I know there'll be a lot of talks on binaries in this conference, so I don't want to talk about the effect on the morphologies and other things, just to see how binaries affect the stellar yield of AGB stars. So this is from a population point of view, not an individual stellar model. So here we see that if we have a single star population, we see that red line, we see initial primary or single mass on the x-axis versus the weighted yield of barium. And then if we have a full binary population, we see the yields go down by about 30%. Now, why? The main reason is that there are just many fewer AGB stars. Okay, almost done, promise. Okay. I did want to actually just briefly mention, oh no, let's go back. I did want to very briefly mention we really need AGB masses. So I will leave this slide for you to have a look at. So please find some AGB masses for us. And this is my final slide, summary. Thank you for your patience. AGB stars are dust element factories. I think we do need more information. We need metallicities, we need better isotopic compositions, we need better surface compositions, and I think we need ways of constraining intermediate mass AGB stars. Thank you. Thank you, Vikele.
Thank you very much. Questions?
Thanks. I got a bit lost with the grid you showed. If you could kind of explain this a little bit again, because I didn't follow the ranges of masses and timescales, and I think there was lots of information there, which was quite interesting. That one, yeah.
Okay, so this shows essentially the fate of an AGB star of a certain mass and metallicity. So the x-axis is the metallicity it was born with, and the y-axis is the mass it was born with. So if it's orange, it has so much mass loss that it doesn't even make it to the thermally pulsing phase. So the fate will be a CO white dwarf still, but it's probably of a lower mass than if it had gone through thermal pulses. If it's blue, it gets to the thermally pulsing phase, but then it doesn't experience any third dredge up. So its composition is just changed by first dredge up alone, which they still have. If it's got those hashed crosses, it does experience third dredge up. So you notice only stars of about 3.3 solar mass and above, and that increases sharply with increasing metallicity, have some third dredge up. So that have some third dredge up, they can make some primary carbon-12. If they've got those orange dots, I know that there's a lot, they also have hot bottom burning. And so the hot bottom burning doesn't shift too much with metallicity, actually. Yep.
Because you mentioned about the production of the S process. So my naive understanding is that it increases with metallicity, but this is a little bit against what you say here.
Because the S process we need stars to have third dredge up in order to make S process elements. But they also should be fairly low mass because of the main drivers is carbon-13 alpha N reaction. So if we only have third dredge up of 3 solar mass or higher, notice by, say, 0.06, it's 5 solar mass. So carbon-13 is, and this almost has some hot bottom burning, maybe not much, but maybe a bit. And so it means that carbon-13 alpha N is unlikely to be the main driver. The timescales are so short as well. So it won't make it much S process or any. And we looked at that in that paper as well.
Thanks.
Thank you. So unfortunately, we are already a little bit late. So
I apologize.
Please ask questions privately to Amanda. Let's thank her again, and get ready with the slides for our next speaker, who is
I think that's
Yoshia Mori, who's talking about constraining the minimum mass for third dredge up in AGB stars with pulsation. Thank you.
Hello, hello. Cool, works. Hi, everyone. I'm Yoshi Amori, or you can call me Yoshi. I'm a PhD student at Monash University in Australia, working with Amanda and Simon Campbell as well. Today I want to talk to you about my research in trying to understand masses of AGB stars, and especially the minimum mass for third dredge up to happen. And I'm trying to constrain these using pulsation characteristics. So this is our problem. So the lowest initial mass that the third dredge up seems to occur in AGB stars seems quite uncertain still. And this is quite important because, of course, the third dredge up will change your surface chemistry, your winds, and your everything you care about for chemical evolution as well. And from observations for the minimum mass to produce a carbon star, it seems to be around 1.5 solar masses, usually from carbon star luminosity functions. And in models, we can reproduce this, but of course, you need to include some uncertain physics, such as convective boundary mixing, etc. What I want to also look at instead is the minimum mass for third dredge up to even happen in these stars. So is it kind of a little lower than 1.5 solar masses? And how low do our models need to go to actually reproduce these stars? So this is our kind of canonical view on how the surface chemistry or the CNO ratio / the spectral type changes over the AGB through subsequent third dredge up events. So you start as M-type, you have some third dredge up, and you can get to S-type stars, so between 0.5 and 1 carbon to oxygen ratios. And these are the stars that I want to focus on today, since they are the ones that show moderate carbon enrichment and also S-process element enhancement, and especially the intrinsic S-type stars. So ideally, these are stars with technetium measurements, as the half-life of this isotope of technetium is relatively short compared to the stellar lifetime. So it's directive evidence of third dredge up happening in these stars. So When trying to estimate some masses of AGB stars, luminosities are very important. And in recent years, the Gaia parallax distances have been very useful. So I've got an example here of looking at the HR diagram to try and constrain some masses of some S-type stars, the work with Shreya Shetye and collaborators. But of course, trying to constrain some parameters, such as effective temperature, can be kind of uncertain for a variety of reasons. Of course, it changes with pulsation, where it is in a pulsation phase. Which reminds me, AGB stars are also pulsating variable stars, of course. And they're observed as long period variable stars, so they come in a lot of different flavors. You have your semi-regular variables, Mira variables, smaller amplitude or giants. I like to focus on the semi-regular variables today. So these are stars usually pulsating in the overtone radial modes, kind of occupying the, I guess, A to C dash sequences on the period luminosity diagram there. And throughout the AGB, we understand that the dominant pulsation mode kind of evolves to lower order radial modes in general. And we do have some models that seem to accurately kind of reproduce these trends, such as the work by Mikhail Trabucki, who'll be talking tomorrow, as well as some efforts in 3D pulsation models. And we can try and make some mass estimates, perhaps, from a combination of these and detailed stellar models, which is what I've been doing. So I have a recent paper out. This is just a broad overview of the steps I went through to get some mass estimates for a selection of intrinsic S-type semi-regular variable stars. So I collected a literature sample of these stars, some stars that have been classified as intrinsic via technetium or some other classification schemes. And then I conducted detailed light curve analysis, so measuring pulsation periods from light curves from Assassin, and sometimes when the Assassin cameras are too good and saturate, I look at light curves from SS and the KWS. I also looked at some driving some luminosities using Gaia parallax distances, as well as a few different methods, which you can see in the paper. And I compare them with detailed stellar evolution models combined with pulsation models from the literature, and finally get a mass distribution. So, some results. This is what the period luminosity diagram looks like with my results for some technetium-rich S-stars. You'll notice a couple things. It looks like there are a lot, but for a lot of the semi-regular variables, they're pulsating in multiple modes at the same time. So you can measure multiple periods. So I have plotted multiple periods here. Some other things is that the Mira sequence for my stars, which are all galactic stars, when you compare it to the Mira sequence for the LMC, there's a bit of an offset, which I suspect may be due to some either some metallicity issues or some composition things, or maybe some issues from parallax distances, but to be looked into further. And in terms of the models that I compare my observations to and my measurements, I combined the Monash evolution code with the linear pulsation model results from Trabucki and collaborators, who also have a very useful interpolation code to combine with stellar parameters. We checked over a model grid of a few different metallicities, and this diagram is just showing how well the observations match up with a representative model grid. Usually the technetium yes stars fall quite cleanly on the grid, but the technetium maybe is a little more scatter. Of course, we use the Vasilias and Wood mass loss scheme on the AGB as well. So the mass distribution of these stars seem to peak quite low and seem to, depending on the type and depending on how you want to express your distribution, seem to peak slightly below 1.5 solar masses. Now, again, I want to stress that the masses that I plot here are kind of the average masses between the model grids of these two metallicities. Since the majority of these stars don't have good or more precise metallicity estimates, we can't quite cleanly constrain their masses as well. It can induce some kind of shift. So we do hope for further abundance measurements for some of these stars. Of course, AGB stars like to be quirky and individual, so I've included a couple here. For example, we have V915 Aquilae, which is a very low luminosity technetium-rich S-type star. Seems to be pulsating in the first overtone mode, and it has a consistently low initial mass estimate of around 1 solar mass, which is quite troublesome when comparing to models of the JoJo. A couple of other stars, a lot of the stars also have long secondary periods, which I haven't mentioned until now. But from this phase light curve, you can see there's a lot of complex behavior happening here, as well as some other interesting stars, such as BD plus 341698, which is one of those bitrinsic S-type stars that show evidence of both extrinsic and intrinsic enrichment. Interestingly, this star I also found to have a long secondary period, around 700 days, which is interesting considering they may also have white dwarf companions if they are extrinsically enriched. Interesting examples. So you might be wondering, what about the Myras? You looked at semi-regulars. So Myras can be a lot more troublesome for many reasons when you're trying to estimate masses. Mainly, I believe, because of mass loss and uncertain mass loss histories. And of course, there's the additional effect of less certain parallax distances and therefore luminosities, as well as some model uncertainties on mass loss prescriptions and some composition effects on pulsation. So there are lots of factors here that you must consider. Something interesting, though, is that when you look at the pulsation, I guess, evolution of the thermally pulsing AGB for different masses, for lower mass stars, they spend more time in lower order pulsation modes, so they are probably more likely to be observed in the Myra phase as a dominant fundamental mode pulsator. So by not looking at the Myras in the sample and trying to estimate their masses, we might be missing kind of a lower mass end of the distribution as well. So there could be more. I'm yet to see this. So this is what I'm currently working on. I'm also expanding this similar analysis to some M and C-type AGB stars and looking at the Myras as well. I'm looking at the sample from Stefan Untenthaler's work. And it also has the interesting technetium-rich M-type AGBs. Sorry, that should say Shreya's talk is today in the next session. And I'm looking at broader selection of light curves and trying to look at the Myras. So that's a bit of a sneak peek. This is, I also have a period amplitude diagram for the sample as well from the light curves. And there's a lot of interesting stuff here. Feel free to chat to me about it if you're interested. I'll just leave up my summary slide here, and thanks for listening.
Thank you very much. Is there any question for Yoshi?
Thanks, Yoshi, for the nice talk. You mentioned about the metallicity effect a bit, which is not yet included because you don't have the observational metallicities. But could you just give us an idea of how your mass peak, the distribution of the peak would move based on these?
Yeah, thanks. Thanks, Shreya. So the idea is, I guess, let's go back a little bit. Yeah, so between these two metallicity grids, I found that it shifted by about 0.1 solar masses, and for lower metallicities, you go to lower masses. So that's the direction that it shifts. So I suppose if more of the stars are more solar, closer to solar metallicity, you might expect the distribution to shift to higher masses. So it's kind of the metallicity is quite important here. But even I did look at a couple stars that do have good metallicity estimates, and even with those, there were still stars that were a lot lower than 1.5 solar masses. So the problem remains.
Okay, thank you.
Cheers.
Time for one quick question more.
So, thanks for the nice talk.
You can use your microphone there. Yeah.
Yeah, thanks for the nice talk. So I had a question about the non-linear pulsation models versus the linear. So in terms of your estimates for masses, for many of the stars, especially when they're thermally pulsing and beyond, like the Myras, you'll have to do the non-linear modeling. So how do you deal with that? And there's quite a lot of mass difference, from what I remember.
Yes. So I've kind of looked at there's Miguel Trubisky's paper from 2021 that looks at Myra and non-linear pulsation models. And so they do have, there is a period mass radius relation that I can tentatively put in to calculate a pulsation period. Of course, I think that there's also a composition effect that is not considered for that. So I'm not quite sure if I don't think I should apply it to at least carbon stars. So that remains still kind of a challenging point. Yeah.
Because I think it introduces quite a big shift in your mass.
Definitely.
Yeah.
Yes.
Okay. Thank you.
Thanks.
Let's thank again Yoshi for his talk. And now we have our final talk of this session, invited talk by Flavia Dell'Agli, titled Unveiling AGB Structure and Evolution with JWST.
Good morning, everybody. It's a great pleasure to be here, to meet you all in person sometimes, and thanks to the SOC, LOC, because I know how much effort is behind organizing a conference, so thank you for this occasion. It's my first time in Chile, so double thank. Okay, well, I'm excited also in this time because I think that is really a thrilling area for AGB stars because thanks to JWST, I must say, for what regards stellar population, we really are enlarging, we are seeing how much we are enlarging our horizons. And I wanted to pick some cases, forgive me for what I've mentioned in this line across the universe that we can see in terms of resolved stellar population and AGB stars. I want to start with the Sextans A. The program in this case is by Marta, and Leeds will talk about it on Wednesday, because when I started my PhD, it was a kind of edge for studies of dust with Spitzer, and well, now is a kind of starting point, because we can easily go to 4 megaparsec, looking at we have already looked at several galaxies with NIRCam with an incredible resolution and seeing so many features in the AGB population at this distance. And then we will have soon the Treasury program by Dan Weitz, who will observe so many galaxies, if I'm not wrong, like 80 galaxies, where we will see nicely AGB stars. And they want to do this because they want to use them to retrieve the star formation history at that distances from AGB stars. So this is really something going on, and this is really the time when people cares about AGB in also other fields that are close to ours. And these kind of studies have been already done in one case that was also mentioned by Martin, the Wiki 18. As far as I know, the farthest from which we have retrieved so far the star formation history from AGB stars. Then soon we will have the Coma clusters vision from the program by Wendy Friedman and Mador that wants to use JAGB method as explained by Martin before to retrieve the distance in an independent way at a distance of 100 megaparsecs. So, well, it's exciting. We will have a lot of data. And today I want to start from this galaxy to give you an example of what we can see and what we can understand probably about the structure of AGB stars and their evolution in this population seen from NIRCam. This is a really nice galaxy because it's a starburst galaxy, kind of analog of the LMC in terms of dimension. Is a dwarf galaxy, is star forming, and in terms of also metal enrichment, it has a similar history as the LMC. This data comes from the FIST program, which is Feedback in Emerging Extragalactic Star Clusters. So this program was meant to study other things, kind of deriving star formation, merging, and information of what galaxies are going to are doing from star clusters. But for free, we have such a nice observation of AGB stars. These data were published recently in the paper by Matteo Correnti this summer. And what we have done is to study this data with a synthetic population constructed over our evolutionary tracks made with the atom code that consider also the star formation in the circumstellar envelope with a stationary wind model to understand how this tracks moves in the CMD of the NIRCam fields or in general in the infrared. We cover a wide range of masses that also correspond to the wide range of star formation epochs, and a metallicity range that then is focused on the ones that can reproduce the data. These are the data. We are studying the filters 115, 150, and 200, which correspond more or less with JHK. Well, from this data, we also have the 444 filter, but from these CMDs, we constructed our simulation. That is this one. And we try to look at the RGB, AGB part of the diagram, excluding the bluest stars that are present because this galaxy is star forming. So, but we are not including in the simulation stars more massive than 8, so we cannot reproduce them. You see that some features appear and we wanted to reproduce them. Here you have an example of how the luminosity function between the data and simulation looks like. And of course, what we needed to create this simulation was to know something about the star formation history. Actually, what was the most recent paper until now was based on optical data on HST that were not reaching absolutely the main sequence turn-off, and neither the clamp. So this star formation history by Saki was derived from the bright RGB and the blue part of the diagram, because at that time they couldn't reproduce nicely the AGB phase, so they decided to exclude it. So what they could retrieve from this HST data was more about the recent star formation history, with a lot of degeneracy for what regard older epochs, older than 1 giga-year, let's say. So what we did is to try to reproduce as much as we can what we are looking at on the opposite, right on the AGB side, and see how much it changed. You can see that we need star formation history high at the early epoch to reproduce the numbers, in particular at the tip of the RGB. So these are stars that have a mass lower than 1 that formed before 10 giga-years ago. And also a star formation history that should be consistent to reproduce this part of the diagram, which is the vertical region where evolves most of the oxygen-rich stars, AGB stars. And then naturally you can have the cloud of carbon stars that appears here. So, well, this is, let me make a warn, and this is still under construction, because what we want to do is to retrieve the star formation history on this NIRCam data, looking at entire CMD and compare our results with the ones that can be obtained with codes like Spira or others codes that usually are used to retrieve star formation history. But well, my feeling is that we couldn't find, we couldn't be so predictive in this area, excluding the AGB stars from the study, and while they can have an effective role in epoch older than 1 giga-year. Now I move to another topic, which is Salto Grande Torre del Paine, or a kind of. This is a really nice place here in Chile, really in the south. I take this as let's celebrate one of the beauty of the Chile, but also because in a way this image reminds me what I found looking more in details in the distribution of the stars of this galaxy. Because if we focus more on the vertical region here that is mostly made of dust-free stars, excluding, I don't know if you can appreciate it, but I'm excluding the blue stars here and also the red stars here. So focusing on the blue. And if I look at the luminosity function, what I see is that this shape that was appearing looking at the entire sample still in a way remain with a shape that recall me this picture with a mountain like a valley and then a fall. Giving other names are common in our field. What we're seeing is a plateau here that corresponds to this oxygen-rich, where oxygen-rich stars evolved, and then a dip at higher luminosity. I was curious about this feature because it's quite, remarked, and also it's present in other galaxies from this program. So something that just turn on. I don't know, probably the battery. Thank you. Thank you. It's not working. No. Everything is green. Now yes. And okay. So I was curious to understand what is happening, because it could be something related to the metallicity, to the star formation history. Who knows? For sure, there is a matter of time scales. Because, well, let's start to see who are these stars. For example, considering the metallicity of this galaxy, we see that stars that are evolving up to this magnitude are all the stars, believe me, all the stars with mass lower than 3 solar masses. Believe me, in the sense that also other masses with lower values can evolve up to here. And this is a kind of ceiling in a way in terms of luminosity and magnitude. And then the stars evolve to the right when they start increasing their surface carbon abundance and producing dust. Then only a 3 solar mass in our modeling, okay, can be, the range of masses can be different, but there is a certain level of mass, a star that can break this ceiling. And if we look at the evolutionary timescales, we understand that effectively all these stars evolve with a longer timescales. Here on the right, we are looking to the time that the stars spend during the AGB phase as a function of their color. So we are seeing that these stars spend much more time in this vertical region rather than at 3 solar masses. And well, of course, we know that this is led by the core mass. But what we are seeing is effectively that all these stars have entered the AGB phase with a similar core mass, while the 3 solar masses is the ones that broke this relation. And this is something that is found also with a different relative enhancement or a different absolute value, but also at other metallicity, lower and higher. So something that can be visible in different galaxies. And the reason is that these stars in the previous phases evolved with the degenerate core in the RGB phase. So they enter with a similar mass in the AGB phase, and they keep this memory while they are evolving in this vertical region. And in a way, it's something that can give you an hang when we study these kind of populations. Then what I've seen is that in our modeling, we can expect to see blue carbon stars, in particular in high mass models, which is, well, absolutely saying is not that surprising because blue carbon stars have been observed also in the LMC. What I want to highlight here is that what is occurring here before the stars move to the right is that they have a higher temperature, effective temperature. So even if they are already accumulate some carbon and they can have a C/O ratio up to 1.5, they are still blue. And in particular, this occurs for more massive stars because this temperature depends on the envelope, the mass of the envelope. In fact, if we look at the evolution of the envelope mass in these different masses and at the C/O ratio, we see that more massive stars enter the C-rich phase with a higher mass with respect to these stars. So this is why we expect to see carbon-rich stars, bright and blue in this sequence. Let's see if we will never confirm or not this vision. And then let's see how these stars move to the red. Because you see that in the data, there is this cloud of stars that we know that these are carbon stars. And you can notice that actually these are detached in a way from the vertical region. And this is really clear from this data, much more than what we could see in with 2-mass data locally, even if some hint was already there. But and this is something that we see also in other galaxies of this program. So this is useful for what Martin was saying about defining the region of the JAGB method the blue side of the AGB region to define it. But let's understand why there is this gap. Actually, we did not we had no difficulties in reproducing it. It was quite a natural, came out of the simulation, because it doesn't depend on the assumption of on the dust formation models or on loss, because it is again a matter of the temperature with which the stars, the effective temperature with which the stars are evolving. If you see here, I marked with empty dots the oxygen-rich phase, then we see some of them are became already carbon-rich, as I said before, and then all these tracks evolves quite rapidly to the red and spend time in the JRGB region. But what is going on here actually is that their effective temperature in this vertical region is always higher than 3,500. And then we have a drop in the effective temperature that determine this quick evolution to the red. If you want to see it better, we can focus on 2 steps of this evolution, and when the star is already a carbon star, so it's not a matter of the type of the star. Within a carbon stars, we are seeing 2 cases. The blue one with a C/O ratio already up to 1.4 and negligible dust. And then after the jump, this is how the emerging spectra appears. The dust has no effect at this stage, is negligible, and while the effective temperature made the difference, and also this treatment of the atmospheres that take into account also all the carbon species, and that leads to jump towards a lower effective temperature. Well, here are my conclusion. My idea on these first studies on JWST stars is that JWST data is that we can really have retrieve hints from the study of AGB population and RGB population to retrieve the star formation history from AGB, let's say from 0.5 to 5 gigayears, and then if we include also RGB stars, of course, we can complete the view. What we have seen is that there is a kind of luminosity ceiling in the vertical sequence of AGB stars that is common in a series of galaxies, and this does depend on their previous history in terms of core mass and how it is, if it is degenerate core mass or not. And then, well, we suppose that we could see blue carbon stars, even in bright carbon stars in the dust-free region, even if they have a C/O ratio quite high, and this can depend on their effective temperature that the star has, if they are quite hot or not. And then we see as a common feature a gap, a rapid transition toward the carbon star region, which can be useful for the future studies applying JRGB method in different galaxies. So thanks for your attention. I hope you can cheer with some good Chilean wine. And okay, I'm happy if you can give me questions and suggestions about these results. Thank you.
Thank you, Flavia. We got back on time. Thank you very much. So if there is any question for Flavia.
Hi, Del Cudi from Chalmers. I don't know if I should say it every time. Okay. So thanks for a very nice talk. So just to make sure that I understand right. Since you're looking at these very not very obscured sources, which we don't expect to be losing mass very strongly, so then the mass loss rate doesn't affect too much what you're getting out, or do you have to assume anything about the mass loss rate to get these results? Like
Well,
mass loss history, sorry.
Well, for what regards the evolution in this region of the diagram, in the vertical sequence, well, I don't expect that we can have a lot of changes in terms of mass loss as soon as they are so blue. Then, of course, we will see how much this can affect the time, for example, that the stars spend in the carbon star stage, of course, or in general timescales for the AGB phase. But I think that what we are seeing are relative behaviors between masses that can change probably also according to the mass loss prescription that we can use. But these are hints that comes from the structure of the stars, the atmospheres, and more than other things like dust formation or mass loss. This is my feeling looking at this data.
Yes, we have a question here.
Hi, Flavia, but somehow I still don't get it. Why is that transition so fast?
Well, I'm not an expert of treatment of opacities in the stellar atmospheres. Our models considers, for example, as mentioned, this opus treatment for stellar opacities. And I think that, for example, for the case I was showing, a role in the molecules like CN that appears is there. So in a way, it's not a direct connection with the C over ratio that we achieve, but like a second order, we have it. We can see it. But it looks like that looking at the effective temperature that we obtain during the vertical evolution is always lower than this threshold. So for sure, it's interesting to investigate more, but it's, I think that is something that is related with this treatment and was not, I mean, we were not looking at this, but it came in a way later.
I think we have time for one more question. Anybody online want to ask a question? If not, I have a very quick question. Do we have any idea of the variability behavior for these groups?
Unfortunately, for this data, no. It's a one epoch sample of observation.
Did you consider by analogy with the LMC if
Well, there are so many analogy really in also, I mean, this kind of plateau and dip can be seen both in the SMC, in the LMC. So why not? I mean, I don't have ins to say no.
Thank you very much. So I guess we can go for lunch or brunch, not sure. So let's thank again the speakers of today's session.
You can leave your stuff here if you want. I was ensured we have security cameras and everything is safe. And the lunch will be served outside. You go towards where the bathroom are, straight, well, follow some of us. And see you at 2:00 then.
Hello? Hello, can I have everyone's attention, please? We are going to start the next session. So I am Amanda Caracas and I'm the chair of this session. Thank you. Excellent. Good. So our first talk today is by Sophie Van Eck, and she's going to talk about tracing S-process signatures in AGB stars. Sophie, take it away.
Thank you, Amanda. So thank you very much to the organizers for allowing me to talk today for this review. Yeah, oh yeah, perfect. Yeah, so I will talk about the S-process signatures, measured ones. We don't like to tell observed ones because abundances are not observed but measured in AGB stars and in the related stars. So what are the information we can get from measurements of S-process elements on AGB nucleosynthesis? Yeah, so the first recognition for AGB nucleosynthesis was the detection of line of technetium 1s by Merrill in '52. And so technetium has no stable isotopes, and it's used actually for medical purposes. Technetium-99, which is on the path of the S process, had a half-life of 2.1 × 10⁵ year. Fortunately, it's not the one that is used for medical purposes. And what is very interesting, I think, is that already in '56, Merrill, in a paper, drew this diagram, where you can see, maybe, well, you cannot see it because it's very small, temperature in this horizontal axis, and then O over C in this axis here, and then S process enhancement in this axis. So basically, the main parameters governing the spectra of S-type stars were already present in that, figure from Merrill. And so this observation of technetium in stars closed the controversy between the primordial nucleosynthesis and stellar nucleosynthesis. And so a few years later, there was the B2FH paper. And so I will not spend a lot of time on this because Amanda made a marvelous talk on the S process operation conditions, on the possible sites, and on the possible neutron sources. So what are the objects that we can use to get constraints on the AGB nucleosynthesis? Well, they are TP AGB stars, of course, also post-AGB stars, despite the fact that the link might be less direct between S-process nucleosynthesis and post-AGBs because things happen in between. Even more things happen for the formation of extrinsic stars, which are binary polluted stars. You can also learn, of course, about this process via the chemical enrichment of the galaxy. And here you can observe whatever stars you want. You have the choice. And there is a last point, which are, of course, meteorites, which are present in the last version of the talk, which I didn't upload. Yeah, so talking about extrinsic stars, oh yes, sorry. So in this talk, I will focus on TP-AGB stars and extrinsic stars. And talking about extrinsic stars, so we will hear a lot during this conference. There are many talks addressing, and even more than that, addressing these stars. So, well, you are all well aware of the binary scenario where from two main sequence stars, the more massives evolve as an AGB and pollutes the companions evolves first not evolved, but contaminated and is observed as a barium dwarf or as a CMP, carbon enriched metal poor star, but enriched in S or RS elements. Then when they evolve as giant stars, they are observed as barium giants, CH, and also CMP stars. And yeah, so those extrinsic stars are present at all metallicities, so close to solar metallicity, they are extrinsic S stars and barium stars, but at lower metallicity, they are CH and CMPS and RS stars. And it has been proven that they are all, well, their binarity rate is compatible with them being all binaries with white dwarf companions that could be constrained from the mass function. So for extrinsic stars, as far as they are concerned, there is a real revolution going on because of the surveys. And for example, I quote here this paper by Chen et al. And so they discovered many S stars actually from Lamost. And they have more than 2,300 new S stars from this survey. And actually, many intrinsic, but 2,000 extrinsic stars, apparently new stars. With this kind of automatic treatment of spectroscopic data, of course, you have a lot of power. Things can be done extremely efficiently. Now, everything is not totally clear to me. So the authors identify 4 spectral regions where they can see that there is a difference in the equivalent width of the features depending on whether the stars are intrinsic or extrinsic. And I clearly see why you would use a zirconium feature, but this feature identified here, it's not totally clear. So I think there is a lot of work still to be done on this kind of data to secure the identification and to understand why there is a statistically significant difference between extrinsic and intrinsic stars on some spectral regions. Concerning Gaia, well, there has been a very interesting work by Contursi et al. In 23. And well, they drew a Kiel diagram, so you have log G and effective temperature. And well, it's coded with the cerium abundance. This is cerium, in color it's cerium over iron. What you can see is, well, the giant branch, and over here there are red stars, so very much enriched in cerium. So these are the TP-AGB stars. What is even more interesting is that here at lower, well, higher gravities and higher temperatures, there are also a bunch of red points here, so stars which are enriched in cerium. We selected those which had a significant cerium overabundance. And actually, there is a high proportion of binaries in the red stars located here, which is significantly larger than a control sample taken from stars which are not enriched in cerium in the same region of the Kills diagram. So just to summarize, these surveys now lead to more and more discovery of extrinsic stars, which were previously discovered in a smaller number. Another very interesting point these years is real-time AGB evolution. And so there is a recent paper here by Laszlo Molnar and also Joyce 2024. And so, for example, they observed some Mira stars like Tiyumi, and they could see a luminosity drop and a rapid decline of the pulsation period. And they identified this as the onset of a thermal pulse. This is not the only example of real-time AGB evolution. There has been previous examples by Zelstra and Uttenthaler, and I think this is extremely interesting, even though it might be difficult to have an ambiguous proof that it's really a thermal pulse. It's extremely interesting to see our favorite stars evolving, directly. So, TP-AGB stars are in fact the only objects where S-process can be probed in situ. So they are extremely interesting, but it's not simple because they are cool, so it means a lot of molecules, and they are variable, so they have dynamical atmospheres. So we need to select the least variable stars, and we need to select the least blended spectral regions. But I'm convinced actually that reliable abundances can be obtained. As you can see from the good agreement that we can get between the synthetic spectra and the observed spectra in oxygen-rich intrinsic stars. And these are fits by Freya. So coming back to technetium, here I summarized the main papers, well, there are 10 or 11, not more, where technetium detections and or abundances were derived in various types of stars, M, S, SC, and carbon stars. Technetium-2 has also been looked for in some stars without success. It's quite difficult to get technetium abundances, but technetium diagnostic, it's not that difficult. We have 3 lines in the near UV, and the diagnostic can be put quite strongly. So I will go rapidly on this. Technetium in M stars. So yeah, some M stars have been found to be unambiguously technetium rich, but I led this for Shreya Shetty's talk just later. Now, S stars. Everybody in this audience knows well what S stars are, but the literature has been polluted for decades, and ChatGPT does not know what an S star is. So ChatGPT still repeats the same things that we have heard and read for decades, that the C/O ratio should be typically 1. So this is wrong for nearly 50 years, actually, from the PhD thesis work of Piccirillo in 1977. We know that S stars have a C/O ratio smaller than 1. So S stars have been studied a lot. So I mentioned here the main papers, starting with the pioneering work by Smith and Lambert. And measured abundance are numerous, as you can see here, and with also several isotopic ratio. And all this work nicely converged to the fact that S-process is occurring radiatively in the interpulse region of low mass stars with the carbon-13 neutron source. So abundances could be derived of S-process elements, including of technetium here. From this NESCANS paper, we could derive some technetium abundances. And when we plot technetium over zirconium as a function of zirconium over Iran, you see that the S stars are located here. And these are the predictions from the models by Lionel Sies. And as you can see, the models nicely go through the observations. So it's interesting because you see technetium starts to increase, but zirconium also increases because it's an S-process element. And at some point, technetium starts to decay also. So there is a kind of decreasing plateau here. And also, this diagram shows the abundance of technetium. So this is the log epsilon technetium as a function of S over Fe, so the S process enrichment. It's difficult to tell that there is a trend, but this is probably because also we see that technetium sometimes somehow decays during the TP-AGB. The HR diagram of these stars is very interesting. So in this HR diagram here, it's a kind of the figure is a bit fuzzy, but well, you can see the different dotted lines here, which are the first occurrence of the third dredge-up from the star evol models. And the triangles are the technetium-rich stars. And the squares are the technetium-poor stars. And they are coded in color with metallicity, the blue being the more metal-rich, solar metallicity, let's say, and the green stars being at metallicity of -1, basically. And what is interesting is that you see that basically all the extrinsic stars that should be technetium-poor are located below or to the left of the third dredge-up lines of the corresponding metallicity. And all technetium-rich stars are located above or to the right of the line showing the start of the third dredge-up. So given all the uncertainties that we have on deriving the luminosities, the temperatures of these stars, given all the uncertainties in the models, I think that this agreement is kind of a nice one. Actually, there are two outliers, extrinsic stars that fall in the TC-rich region, and we still don't know whether there is some uncertainty on the Gaia parallax, or we're still trying to understand that. As was mentioned before this morning, some stars were found to experience third dredge-up, some low mass stars, so with masses as low as 1 solar mass stars. And so all these works comes from Shiaz Chettier PhD thesis. Oops. Yeah. So now talking about technetium and niobium. So technetium decays to ruthenium, and zirconium-93 decays to niobium-93. And actually, you can see on blue and red the theoretical predictions of these, the evolution of technetium and of zirconium over time. And when you try to confront this with the determined abundances, you can find a time. Actually, these isotopes allow to do cosmochronometry for S-type stars, more precisely to measure the time elapsed since the onset of the third of the S-process nucleosynthesis. And so this has been done. These times have been derived and correlate quite well with the infrared excess, which can be seen as an evolutionary proxy. So again on technetium and zirconium. So I just wanted to show you the spectra. So this is one star, and you can see that when it has a normal niobium, it is enriched in technetium. And another star, which has an enriched niobium, is not enriched in technetium. This is simply because when the S process is producing technetium, zirconium-93 did not have time yet to decay into niobium-93. So niobium-93 still has its solar abundance. And we can see this very well in this zirconium-niobium plane, where you have the TP-AGB stars who are located here, which are located here, with an enhanced zirconium, but no niobium yet, because zirconium-93 did not decay yet to niobium. So there is a solar value of niobium. In extrinsic stars, the binary ones, the polluted ones, zirconium-93 had time to decay into niobium-93, which is monoisotopic. And so you clearly see the niobium abundance increase. So actually, zirconium, technetium and niobium are two ways to identify extrinsic stars. This diagram has been reproduced since then in S stars, barium stars, CMPS stars, CMPRS stars, and actually this trend of extrinsic sequence here is seen in all these type of stars. Yeah. And this diagram also allowed to identify two stars, one located here and one located here, which are enriched in, especially this one, you see, it's enriched in niobium, though it's enriched in technetium. So it has the properties of both intrinsic and extrinsic stars. So they were called bitrinsic stars. And so actually they are located here in this binary evolution diagram. So this is when the polluted companion reaches finally the TP-AGB and produces technetium. So this diagram, this very same diagram, has been used to determine the S-process separation temperature. Why? Because actually, if I go back, yeah, maybe I go back to that slide here. If you take this, this should be a straight line. I will discuss this in a few minutes. And if you take the y-intercept of this line, actually, because of this equation here, this will give you omega star, and omega star is the ratio, the isotopic ratio of zirconium over zirconium-93. So we are not directly able to measure the isotopic ratio, but thanks to the measure of niobium, we are able to have information on this isotopic ratio. This was used to derive the S-process operation temperature, computing this isotopic ratio from S stars and comparing it with nuclear computations. And this confirmed the neutron source. However, there has been a very interesting paper recently by Villagos et al. And so this was done only on a sample of a few stars that we had at the time. In these papers, the authors considered 180 barium stars. So of course they have a lot of information and of abundances. And well, actually the conclusion they reach is not, the situation is probably not as simple as we assumed in this figure here. Because probably, well, there is no isothermal line here, and even probably there is no steady state S-process. The S-process does not reach the steady states, and this hypothesis was actually necessary to reach this conclusion and these temperatures. So, whereas for some stars it does work, and it leads to a temperature compatible with the one obtained here. For other stars, you really need to relax the steady state S-process hypothesis. So I think it's really interesting that this zirconium niobium problematic can lead to to really details of S-process nucleosynthesis. Yeah, rubidium. Well, so I will go very quickly on rubidium. So you know that there was a controversy with very high rubidium abundances, which were at odds with the theoretical predictions. But then new models by Plaise and also by Zamora showed that considering circumstellar absorption, winds, non-LT, and extended atmospheres, it was basically solving the discrepancy between the predicted and the measured rubidium abundances. And so rubidium has been measured in carbon stars. So this is a paper by Carlos Abia, and also in barium stars. And basically all these measurements avoid the intermediate mass AGB location, and so confirm that all those stars experienced S-process from low mass stars or were polluted by low mass stars. Now, S-process and C over O discrepancy. So we all know that, okay, and yeah, there was a mention this morning of a star reaching a huge C over O ratio, but maybe more because of a low oxygen abundance. But we all know that it's difficult to reconcile the C over O from the observations, from the measured C over O, and from the theory. Well, actually, there is even another problem. The problem is illustrated here in this diagram by Shriya. So if you have the C over O here as a function of the total S over iron, S over iron quantity, you have S stars in blue here and carbon stars in green here. So with C over O slightly over 1. The problem is that model predictions, model predicts a large increase of C over O very rapidly, so that at the S process enrichment measured in S stars, the C over O ratio should be extremely high, which it is not, because there are S-type stars with C over O smaller than 1. And so here, measured abundance contradicts and still contradicts with the models. Yeah, so there has been some studies of S process in SC stars. So SC stars are the ones with oxygen equal to carbon. And so they show zirconium oxide bands for the SC ones, but very weak ones, and the CS ones, because if you see sometimes in the paper there are SC and CS stars, the CS ones show C2 bands, weak C2 bands, but you do see zirconium oxide bands in SC stars. And so they are intrinsic, and the carbon-13 neutron source has been demonstrated to operate in those stars. And there are two prototypical atypical objects. Well, those SC stars are really weird. UY Sun, well, there has been dust formation episodes observed in Stanford, and BH Crew, which is another case of real-time AGB evolution, probably. Okay, so for carbon stars, I will not extend a lot. There is just a recent paper by Carlos where he has studied carbon stars in 9 open clusters. And so he derives that the mass of these objects are between 1 and 5 solar masses. So actually you can reach carbon stars, this was mentioned before, with quite high masses. Fluorine, well, I will go quickly on this because I want to go to binarity. So, and to CMP stars. So you know that there are CMP S stars compatible with all being binaries, and CMP RS stars. And all of them also seem to be binaries. So carbon enrichment at low metallicity is very ubiquitous. As you can see here in this Yoon study, the fraction of CMP no stars, so carbon enriched metal poor stars with no S process enrichment, is decreasing with, this is metallicity, but is apparently of 1, so very high at extremely low metallicity and decreases. Whereas the CMP S stars have a kind of constant 10% occurrence rate with metallicity. Before going further on these CMP stars, which are low metallicity stars, I would like to stress that non-LTE abundances are very important to take into account. For example, here in this lead over iron as a function of metallicity figure, you see that you can change the abundance by 0.4 dex simply considering non-LTE lead abundances. And this really helps to reconcile the measured abundances with here the R process model. So it's extremely important to take these non-LTE effects into account. Now, CMP RS stars are stars enriched both in S and R process elements. So actually, there are two scenarios, either two independent pollution events or a single astrophysical site, the I process. So the I process was already mentioned, and these figures were shown, so I will skip rapidly. Hybrid RS patterns were found in these studies here. So there are many stars with hybrid patterns were found. And so people wanted to start to classify them. And to classify them, well, there was this paper by Hansen et al. Where they tried and they showed that CMP S stars have larger light S over heavy S elements than CMP RS stars. And this was also recovered in this Karim-Cozy study. Another way to classify them, to try to understand which ones are S stars and which CMP S stars and which ones are CMP RS stars, is to fit with models and to see from the models which models are fitting best the abundances. And this was done in this Karim-Cozy paper. Another way still to classify is to put an S process element, an R process element here, And so you have regions which are populated by S-process enriched stars, R-process enriched stars, and in between you have the RS stars. But you see that the delimitation is a bit fuzzy. Another way to try to classify those stars is to use an abundance distance. So given the abundances measured in a star, you compute the distance to a typical solar R process, believed to be a kind of universal reference, though we well know that the R process is not universal, but it's the best universal reference we have. And this way you can also distinguish between CMPS and CMP-RS stars. And the last way and last method to differentiate between those type of stars is using isotopic ratio. So from the paper by Arthur Chopin, it has been shown that several elements and the isotopic ratio differentiate actually the S process from the I process. Of course, measuring isotopic ratio from atomic lines is extremely difficult, but whereas the maximum isotopic shift is of the order of 2 milliangstroms for lines. When you have lines affected by hyperfine splitting, then you have a much wider broadening of the line of the order of 50 milliangstroms. And this broadening actually helps us to define a fraction of the odd isotopes over the total isotopes. And for example, this is what we have done here using a prototypical S-process enriched star, R-process enriched star, and RS star. We are able, from the line profile, fitting the model of the matching F odd, so odd ratio, we are able to recover actually whether the star is S process or R and I process. There is an indetermination between R and I process actually from the barium isotopic ratio, but other isotopic ratio will help to solve this discrepancy. Now, a last way to classify those stars is using thorium. So there has been a claim by Gull et al. Of thorium detection in a CMP-RS star here. As you can see, the thorium line is very much blended by carbon-13 CH, actually. And this type of detection should be repeated because to be secure, to be sure that we really observed, measured thorium in a CMP-RS star. And actually, it does not even allow to differentiate between S and RS process because the I process has been shown to be able to produce thorium also. So this observation is to be interpreted with it is not even sure that it will allow to differentiate between the different scenarios. Finally, a last way of discriminating between the CMP-S and RS star is tantalum. And here I show you the detection of tantalum in different type of stars, CMP-RS stars. You can see that we have very clean tantalum lines. Well, we are in the UV at 3,500 angstroms. And the very high tantalum abundances is very discriminative between the I process predictions in red and the S process ones in blue. So measuring tantalum abundance might be a very interesting way. And I leave my conclusions here. Thank you for your attention.
Unfortunately, we're out of time, but I can maybe take one very quick question, if there is one in the room, very quick. Okay, maybe I think we move on. Oh, sorry, there's a question. Oh, it's very hard to see behind. Sorry, Hans.
So, Sophie, what is your evaluation of the problem between the carbon C over O, let's say, and the S process overabundance? Is the C over O wrong, or is the S process overabundance wrong, or are the models wrong?
Well, what I can say is that for the oxygen-rich stars that we are observing, the molecular bands would not form if the C over O was not smaller than 1. So definitely they have C over O smaller than 1. There is an uncertainty on the oxygen abundance, which is extremely difficult to measure in S-type stars. So this might be part of the problem. And then I think that we have to investigate on the also from the model side what would occur. But there is still this discrepancy. And the problem is that, okay, sometimes we say, yeah, but the very high carbon abundance stars, we don't observe them because they are obscured. And that might be, maybe they are obscured and we don't observe the very high carbon abundance stars. But here we are not at very high carbon abundance. We are at C over O smaller than 1, so for oxygen-rich stars. And we already have this discrepancy. So there a problem.
I think we have to move on. Thank you, Sophie. So shall we thank her again? So our next talk is by Diego Vescovi, who is going to talk about, let me just find his title, Tracing S-Process Signatures in Pre-Solar Grains from AGB Stars. Now, Diego is remote, so he'll be sharing his talk, we hope. So Diego, please, can you share your slides?
Can you hear me?
We can, yes.
Okay.
I'll give you a warning when you have 5 minutes left.
Yes, but I do not have the option of sharing habilitated, I think.
Then that's not, I don't know how to change that. Okay, it's being looked into.
Yep.
One minute.
No, there is no button. No, there is no button with share, but otherwise I can tell you when switch slide.
Do we have the slides? Did he upload the slides?
I uploaded it.
Maybe we can just show the slides, and Diego, you might just tell the people to move forward.
Yep.
Okay, yeah. All right, I'll give you a 5-minute warning.
Yes,
for a 15-minute talk, no, 12-minute talk. Okay.
So good afternoon, everybody, and sorry for not to be there with you, but I want to thank anyway the organizer for letting me present today, even if I'm at home. Today I will present something related with the presolar grains and the possibilities that arises from using data from presolar grains to constrain the physics of AGB stars. Next slide, please. So we have seen in the previous talks by Amanda and Sophie that AGB stars are important contributors to the production of EV elements in the universe through the slow and intermediate process. Next slide, please. But in the following, we'll focus on the S processing in AGB stars. In these stars, we have two main neutron sources active, the neon-22 alpha N reaction that is active at the base of the convective thermal pulse, and the carbon-13 alpha N reaction that is instead active during the interpulse phase and requires the presence of a thin layer rich in carbon-13 in this region. And the solar grains could be useful in constraining both of these neutron sources. Next slide, please. No, you can skip this. I think this one is the old one. Okay. Presolar grains are formed in the cool layer of AGB stars. I will focus on the silicon carbide grains that are supposed to form during the carbon-rich phase of these objects, and these grains eventually are injected into the interstellar medium and became part of the molecular cloud from which the solar system was born. And these grains can be found here at Earth when analyzing meteorites that have reached the Earth billions of years later, the formation of the solar system. So through laboratory analysis, we can get precious information about the isotopic composition of these presolar grains, in particular of EV elements, with an accuracy of about 10%. That is pretty much low. Next slide, please. Regarding silicon carbide grains from carbon-rich AGB stars, we can divide roughly the grains in 3 groups, as we have seen before in the Amanda's talk. The mainstream grains represent the vast majority of them, around 90%, and then we have and that are supposed to come from AGB stars with close to solar metallicity. And then we have the Y and Z grains that instead are supposed to come from lower initial stellar metallicity and or higher initial masses of for AGB progenitors, because the Y grains exhibit high carbon 12 over carbon 13 ratio. That is what we expect from low metallicity AGB stars, and the Z grain instead have a pretty low delta values for silicon 29 and high content of silicon 30. That is supposed to, let's say, be the signature of the activation of the neon 22 alpha N reaction in the AGB progenitors. Therefore, they should be more compact objects. Next slide, please. And next one again. Okay. In the past, we have used successfully mainstream silicon carbide grains to constrain the formation of the carbon-13 pocket. As you can see in this plot, the problem here was to fit, to reproduce, to provide a good match to the strontium 88 versus barium 38 ratios, and that could be only possible if one consider a model in which the answering carbon-13 pocket have a quite flat profile with a low abundance of carbon-13, and this was shown to be possible with introducing a magnetic mixing in the models. Next slide, please. No, next one. This is the oldest one. Again. No, this is the wrong presentation, sorry. In any ways, regarding the Z1 grains, we basically have an additional problem because the molybdenum isotopes can provide you some further constraints on the efficiency of the neon 22 alpha N reaction. In particular, the molybdenum isotopes show a linear trend that can be followed only if the parent AGB star is a low mass AGB star, meaning that it do not activates efficiently the neon 22 alpha N reaction, because in this way you basically are able to follow the trend. But if you say so, then you cannot explain anymore the silicon 30 abundance, the high content of silicon 30 that you can find in Y grains, as I've shown you before. Next slide, please. Next. Again, next. Sorry, next one. Again. Again. Okay, now I will present you some new results about a new data set of grain data that have been provided by Nan Liu at the Boston University. So you can see here, this new set of data comprises both mainstream grains and seed grains, okay? And you can see that there is a clear smooth trend with nickel 60 versus silicon 29, sorry, in agreement with what we expect from GC model with the red line. That therefore tells us that these ratios are inherited basically from the interstellar medium that is a byproduct of a galactic chemical evolution, a homogeneous galactic chemical evolution. Instead, at about -50 per mil, there is a quite large enhancement in nickel 60 that therefore claims for an additional process different from the uniform GC. Next slide, please. So if we think about possible nickel 60 variation, then a possible contribution could be by the parent AGB star itself, could be radiogenic decay of iron 60, but if you consider low mass stars, then it is impossible to produce a high amount of iron 60 unless you activate fully the neon 22 alpha reaction.
So Diego, you have a couple of minutes left, just to let you know, about 4 minutes.
Yes, I will be fast. And then also the nickel 60 overabundance is impossible to produce in a quite amount via the standard S-process nucleosynthesis, because usually you produce more neutron-rich isotopes. And then the last option is that this large nickel 60 variation is due to some kind of stochastic GC phenomena, namely that some particular nucleosynthetic source have polluted the interstellar medium from which the parent AGB stars of these particular grains were born. Next slide, please. So we analyzed the different possible scenarios, and we got that the best pollution scenario is the one that a close-by supernovae type 1a has polluted the interstellar medium from which these progenitor AGB stars were born. Next slide, please. Because basically it inject only excesses in nickel 60 without introducing excesses in other nickel isotopes. And then, considering this possible pollution, we computed a model in which the solar scale initial composition of the parent AGB stars is mixed with some amount of type 1a supernovae material in order to match the nickel 60 abundance. You can see here in the plot the yellow line, okay? And if you do so, you even get an increase initial titanium 48 and silicon 28 abundance that put your model here in the plot above, in the plot at the bottom with the yellow line. The model is right in the right place. And additionally, if you consider a pollution by type 1 supernovae, then you increase also iron 56, and then you change your S-process efficiency because you start producing a lot of light EV elements at the expense of more EV elements, and there you can find in the upper plot that the yellow line produces much more nickel 64, for example. Next slide, please. However, the supernova type 1a scenario is not suitable to reproduce the silicon 30 excesses because it basically do not produce these excesses. So we still need an additional distinct nucleosynthetic sources for this isotope. Or next slide, please. we recover to lower metallicity and higher mass AGB sources, but as we have seen before, this introduces some shifts in some particular molybdenum, barium, and strontium isotopes that are not in agreement with the data. And so there is still this problem of explaining the the silicon-30 excesses if we adopt a model that fit strontium, barium, and molybdenum isotopes. So next slide is the concluding one. So we have seen the potentiality of per-solar grains to constrain AGB modeling in both the main neutron source, the carbon-13, and also the secondary one, the neon 22 alpha reaction. We have seen that there are some a few percent of AGB grains exhibits deviations from the galactic chemical evolution trend that is in agreement with a pollution scenario from type 1a supernova to locally to the interstellar medium, and that there is still active the problem of silicon-30 excesses in Y and Z grains. Because it is a dot with molybdenum, barium, and strontium isotopes. So I concluded, and thank you for your attention.
Thank you. Well, we have time for one question. Can include online. I'll have a look. If there are no questions, anyone online for a question? Okay, let's thank Diego again. We can move on. Our third talk is going to be by Lionel CS, who will talk about the intermediate neutron capture process. It might happen in AGB stars. Thanks, Lionel.
Yes. Okay, it works. Okay, well, first, I wanted to thank the organizers for inviting me. And today we'll report on our study of the high process nucleosynthesis in AGB star. Well, I have to say that most of the work was done by Arthur Choplin. We've heard his name quite a few times already, but also in collaboration with Stéphane Gorielli and Sébastien Martinet. So the I process, I stands for intermediate. So it is intermediate between the S process that we heard before this morning. It's characterized by neutron densities between 10 to the 6th and 10 to the 12th. And as we've seen, there are two sites, either during the pulse or during the interpulse. And the typical time scale for the S process, the radiative S process, is 10 to the 4th years. On the other extreme, you have the R process that goes to neutron densities up to 10 to the 24th. And that takes place in hydrodynamical events like neutron star mergers or core collapse supernovae. And the time scale is typically 1 second, hydrodynamical time scale. And the I process just lies in the middle. And as I will describe, the characteristic time scale is typically a few days, and the neutron density is 10 to the 15th. So how do you produce these high neutron densities? Well, the recipe is quite simple. Huh? You just mix some protons into a convective helium burning shell, and then you have that chain of reaction that eventually forms C13, and you have the C13 alpha N that produces the neutrons. Concerning the astrophysical sites, well, massive stars, there have been studies reporting proton injection in massive stars, but also in low and intermediate mass stars, and this is the focus of this talk. So the various studies in the past 30 years have reported this proton injection in very low metallicity stars or POP3 stars. I will explain why, either during the core helium flash or at the beginning of the AGB. This injection can also occur in late flashes, late thermal pulses, but also if you have an accreting white dwarf. So how does that work? So this is a Kippenheim diagram that shows, well, this is the mass coordinate, the center of the star is the bottom. This is the model number, but that's a proxy for time.
and the gray area is the convective shell. So this is a representative model. So one solar mass star at a metallicity minus 2.5 in terms of FA over H. And so you have initially, well, the pulse that develops, and eventually, because we are at low metallicity, it can cross the mean molecular weight barrier and starts to heat the protons, to reach the hydrogen burning shell. So at that stage, protons are engulfed, they are burned on the flight, and they first are captured by C12, so you form nitrogen-13, that then decays in something like 10 minutes to form the C13, and the C13 is advected by the convective motion at the very bottom of the pulse, and here the temperature is very high. It's something like 250 million degrees compared to the 90 million degrees that occur in the radiative S process in AGB star. And this is because of this very high temperature that you can reach very high densities. When the protons fly, well, when they are engulfed, the energy is mostly deposited in the region where the nuclear timescale is equivalent to the convective timescale. And here energy builds up, so you have accumulation of energy and eventually a temperature inversion. And we know from star evolution classes that with the Schwarzschild criterion, if you have a negative temperature gradient, then the layer becomes radiative. And you have here the split of this convective pulse. You see that it separates into two zones. You have a bottom one, convective zone, that will never reach the surface, and you have an upper one. And because there is a lot of energy that is released by this injection, something like sometimes 10 to the 10th, so our luminosities are generating this injection, there is some structure readjustments, and eventually what we see is that the convective pulse will eventually merge with the envelope. And the high process elements which were generated just before at the bottom of the pulse and before the split, they can eventually reach the surface of the star. So not only high process, oops, how does that work? Oops, sorry. Yeah, so not only high process elements can reach the surface, but also carbon. Remember, that's a helium burning shell. So you bring a lot of carbon. And in this one solar mass star, we enrich the envelope so much in carbon, then the opacity rises, and that boosts the mass loss, and you actually lose the envelope before the occurrence of the next thermal pulse. So the AGB evolution is truncated in this case. If you take a more massive star, well, the dilution factor is less, so the consequence on the mass loss are less dramatic. You can see, well, you have the injection here, and then it follows by, well, the standard TP-AGB evolution resumes, and you can have a mixture of I and S process elements in that case. So which star do actually suffer from this proton injection? So what is shown in this plot, so this is the initial mass of the star, this is the metallicity. The different symbols are a collection of studies that reported this proton injection. And very important is that all these models did not include any extra mixing. And what you can see is that the mass range, well, the region in this plane where proton injection occur is limited to low mass star, typically less than 3 solar mass, and relatively low metallicity in terms of FA over H, less than -2. So what we did is to analyze what is the impact of implementing some extra mixing. So we did that by including some overshooting. This is a classical recipe in star evolution, an exponential decrease of the convective coefficient. And we added the overshooting at the base of the convective envelope and at the edge of the pulse. And what our study showed is that the only parameter that is important for the occurrence of this proton injection is the amount of overshooting at the top of the pulse. And as you can see here, so this is the same diagram as before. This is the mass, but here it's not FA over H, it's Z, it's the metallicity. So this is the zone that we saw before. And you see that if you increase the mixing, so the green and then the blue and then the red, the more mixing you add, the larger the parameter range allows the proton injection. And very interesting is that you see, for instance, at 1 solar mass, if you had a lot of mixing, that eventually you can have that proton injection at almost solar metallicity. And that is something that could explain the J-type stars that was mentioned earlier. So what about the nucleosynthesis? So this is the typical charge. This is number of neutrons, not number of protons. The blue is the S process path, and the square are the stable elements. So you follow the value of beta stability. The green is the R process, so you are in the very neutron-rich region, and the I process lies in the middle, you see. And just to illustrate, this is the production of some isotopes, so we use quite big networks to do that. And I will focus on europium because this is a tracer of the R process. And you see, well, the stable isotope of europium are the 151 and 153. And we see that we mostly produce during this process the 159. And eventually, well, what happens is that when the neutron source shuts down, then everything decays back into onto the value of stability, and that's how you produce these stable elements. What is the characteristic of the I process? So here I show, this is the elemental abundances as a function of Z. This is the overabundance, X over FA. And in blue, this is the typical S process for the same star at the same metallicity that does not experience this proton injection. And in black, this is the I process nucleosynthesis. And what we can see, in short, is that we produce less light S elements like strontium, yttrium, or zirconium, but we produce more heavy S elements. And in particular, we produce a lot of tantalum and xenon. Okay, so that may be traces of the I process nucleosynthesis. In terms of yields, so this is the yields that we obtain. So it is the same mass, the same overshooting parameter, but different metallicities. And what we see the same trend as for the S process. So mainly when you increase the metallicity, you produce less and less heavy elements. This is because you have a lot of iron, and all the neutrons, instead of building heavier elements, they are captured by iron. So you stop the flux, the neutron flux, and you produce only, light elements. Another characteristic of this nucleosynthesis is the massive production of lithium. You see, all these processes, irrespective of the metallicity, produce a large amount of lithium. And that can explain also the J-type stars. They have no S process enrichment, so that's the black line, but they have very high lithium. Also, these models have C13 over C12 ratio relatively low. That fits the J-star scenario. Another feature is that under certain circumstances, we can also produce actinides. So very heavy elements. They were thought to be only produced during the R process, but actually in this I process, under certain circumstances, you can produce these actinides as well. So do we observe these I process products? Well, the best test bed is the CMP-RS stars that Sophie mentioned. So they show overabundance in S and R process elements. So they are intermediate between S and R. And what we did is for all these stars, we try to produce these abundances using either only the S process abundance, only the R process, a mixture of S and R, or using the predictions from our models. And we did a chi-square between our predictions and the observed abundances. And we see that the I process, which is the red line, has the lowest chi-square. So that can reproduce relatively well all these stars. And also in terms of dilution, that is consistent what we would expect, the pollution in terms of what is the amount of mass that we observe, because the CMP stars are all binaries. They inherited these abundances, either from the primordial scenario or by the pollution by a companion. And that leads me to the conclusions. So the I process critically depends on the amount of mixing that you have, and especially at the top of the pulse, you can or not trigger this I process. In terms of nucleosynthesis, you tend to form more heavy S elements, less light S elements. This scenario can nicely explain the CMP-RS stars, and also could explain, I don't have time here, but to explain the J-type stars. And what is interesting is that you can also lead to the production of actinides, very heavy elements. But everything that I showed here is very dependent upon the mixing. Depending on the mixing, you have or not basically the proton injection, but also on the nuclear uncertainties, because we are far from the value of stability, and nuclear uncertainty starts to be relevant. Thank you.
Thank you, Lionel. We have time for some questions. I see one behind you. Yoshi, if you want to grab a microphone.
Hi. Thanks for the talk. That was really good. Just on the topic of the lithium production in the J-type, well, like that may be representatives of J-type stars. How do you have an idea of like the lifetime of the lithium in those models? Is it destroyed quickly, and can that explain like observed rates of J-type stars?
No, it's not destroyed. It's produced during the engulfment, and then it is in the envelope. So unless you have some hot bottom burning or something, it will remain in the envelopes. So you need to reach at least a few million degrees at the base of the convective envelope to destroy it. But if not, no, it will remain there. Yeah.
Other questions? We have time for another one or two. Devika, please. Don't forget to introduce yourself as well as
yes, okay.
When you ask your question.
Thanks,
Thank you.
Amanda. Hi, everyone. I'm Devika from Macquarie University. Thanks, Lionel, for that nice talk. I have a question on lead. So you had a plot there where you had all of the, for different models, for different elements. And my question is, have you sort of compared the I-process abundances that you predict with lead abundances from some of the SEM stars or post-AGB stars, or because lead's always a bit tricky, and I was just wondering if you can comment a bit on that.
I didn't look specifically onto lead. What we did is to do this chi-square minimization to try to find which reproduces best the CMP-RS stars. We didn't look at the other ones because the CMP-S stars or post-AGB stars that do not show enhancement in R-process elements. I don't think this process will work for that, because we need also this very high, this specific nucleosynthetic signature for that. But lead, yeah, yeah.
All right, let's thank Lionel again. I think we have to move on. Thank you. The next talk in this session is Shaya Shetye, who's going to talk about a multi-wavelength view of technetium-rich stars and their role in stellar evolution.
Hello. Yeah, I think you can hear me better now. Waiting for my slides to be there. Yep. Okay, cool. Hello, everyone. Yes, I will be focusing, I'm Shreya, and I'll be focusing about M stars. Thankfully to Sophie and Yoshi, who already talked a lot about my S stars work, so I can really skip it and go to M stars. I have a traditional overview of what I mean when I talk about the M stars or S stars. So traditionally, this is a spectral classification. We know the M stars, they are stars enriched with titanium oxide bands, while S stars show both titanium oxide bands as well as zirconium oxide bands. Sophie already touched upon the carbon over oxygen ratio of these stars. M stars show solar carbon over oxygen ratio, while S stars have a slightly higher carbon over oxygen ratio, but still less than 1, which explains their molecule, oxygen-rich molecule nature. Sophie also already mentioned about the intrinsic extrinsic stars and how we distinguish them. It's thanks to technetium. Technetium allows us to identify genuine thermally pulsing AGB stars and distinguish them from their extrinsic counterparts. So these are extrinsic S stars, barium stars, the carbon enhanced metal poor stars, etc. So I am very interested, of course, in technetium because I really want to study these TP-AGB stars. And the focus of this talk is going to be stars, M-type stars, showing technetium features. Now, these are not very new. Actually, they have been known for 40 years or so. And actually, from the Vienna group, there has been a lot of work by Ottenthaler, by Lebzelter, on the pulsation characteristics of these technetium-rich M-type stars. However, what I want to focus is on their spectral characteristics and how different or not they are from S-type stars. So here an example to prove you all that these are all indeed technetium rich. You have the two technetium lines and you see clear absorption features at both these technetium lines. So it's really comparable to what we see in technetium rich S-type stars. The goal was very clear for our study because we had many open questions to really understand. So we understand a lot the pulsational characteristics of these M stars. They are Myra type variables, some of them LPVs. So these are pulsating stars. They definitely show technetium. But how are their other characteristics different than the S-type stars? What is the evolutionary status of these technetium-rich M stars? Are we really looking at the onset of the third Rajab? Or is it just stars which have been going through several episodes of third Rajabs and thermal pulses? Then, of course, how different or not their S-process abundance profiles are from the S-type stars and the carbon stars. And also, one of the open questions is, besides technetium, do they show any other S-process elements? Because they definitely show technetium. If they would show significant zirconium, they would be classified as S-type and not M-type. So what is really happening? Is it only technetium? Is it other S-process elements as well? And what is the evolutionary status, et cetera, et cetera. So to answer this these questions, we started with a spectroscopic study of a relatively large sample of M stars. So we started with almost 57 M stars in general. We did not know their classification scheme from beforehand. And this was done using, of course, the Hermes spectrograph at Mercator telescope. So we collected high resolution data of these stars. And the idea was very simple. I mean, you want to do the spectroscopic analysis to see their abundance patterns, to study their evolutionary characteristics. To give you an overview of what we found, so this is the full sample. Of course, there are 18 stars or so for which we couldn't really identify their technetium. I mean, we couldn't really detect well the technetium, basically because of the quality of the spectra. But for 39 stars or so, we have a clear classification if they are technetium rich and technetium poor. And these are the stars which I'm going to focus on in the talk. Of course, this was done basically by a visual inspection of the kind of plot that I showed you. Battery down. I didn't press anything. Should I try again? Hello. Is it better? I don't know if this one works either. Yeah? Okay. Oh, now it does, definitely. All right. So the technetium detection or not, it can be really done by a visual inspection of technetium lines. Because if you do have technetium, you see clear absorption features like the plot that I showed and also Sophie showed previously. But of course, we were interested in, are these spectral lines, are the characteristics of these lines any different from the S-type stars technetium lines? So on the right, you see plot of technetium line indices, which are calculated for two different technetium lines. I will try not to go too technical about it, but you see clearly two zones, the technetium poor zone and the technetium rich zone. The S stars for comparison are also plotted here, as well as synthetic spectral indices are plotted for different technetium abundances so that you can see how the properties of the stars, so the temperature, metallicity, etc., affect also the movement of stars in this kind of diagram. The technetium poor stars, the technetium rich stars are very well segregated. You can also see that we have kind of a detection upper limit or lower limit in terms of the abundance of technetium that you do need to have in order to detect these lines in the spectra of these stars. This detection limit is affected by the temperature, so if the star is cooler or warmer, and also by some other properties, but that is marginal. The major effect is actually temperature. But any which way, we didn't see any difference in the S and M stars, the technetium-rich S and M stars, technetium line indices. So they basically all overlap. There is a little bit of a scatter in the line indices for technetium-rich M stars, and that actually comes from their variability, because they are highly variable, as I mentioned already, and this is why the spectral lines are also kind of affected. But technetium features-wise, these guys are not any different than the technetium-rich S stars. Now comes the main key difference, right? The segregator of these stars was their molecular features, was their zirconium oxide and titanium oxide band. And what you see here is that we computed band indices for ZRO and TIO. And have plotted this with S stars here in open symbols, while the M stars are filled symbols. On top, again, the tracks that you see are the same indices computed for synthetic spectra. You see that the S and the M stars, they form a complete separate sequence. You see that there are technetium-rich M stars in this zone, which show actually quite significant ZRO band index as well. So strong ZRO band index as well, but they show significantly higher titanium oxide bands. So this classification issue might not be that these stars don't show any ZRO bands. It might be that they show way stronger TIO bands compared to their ZRO bands, and they do show some signatures of S-process enhancement apart from the technetium because of the zirconium there. So this was very interesting to see that this classification scheme that we have traditionally, maybe, yeah, we need to revisit it and really need to understand the properties very well. Also, what is very clear when comparison with the synthetic spectra is that these technetium-rich M stars are typically a bit cooler. They are cooler. They are also Myra variables, as I mentioned already. So that's also explains, I mean, their coolness. I will quickly go through the evolutionary status because it's a mess to locate these guys in the HR diagram because, again, of their variability. So they move around here, as well as deriving their effective temperature luminosities was quite complex. But the takeaway is that they have similar luminosities as technetium-rich S stars, and they are all located beyond the predicted onset of the third Rejop. So, okay, evolutionary status-wise, it's not super weird. We do detect stars that show traces of third Rejop and that also lay beyond this predicted onset. Great. But luminosity-wise, they show the similar luminosities as S-type stars, and we did not even try to attempt to derive masses from here because, as I mentioned, the stars move around here, so that's not maybe the wise way of deriving masses and comparing the masses with those of S-type stars. However, the traditional sequence of M to S to C, we know that this works chemistry-wise, but on the HR diagram, it does not work, and it is not the case, even when comparing to the stars of the same metallicity, etc. The last thing that I do want to touch upon is the theoretical predictions. How is it even possible to make these stars, to have stars which show technetium, but do not show significant zirconium enhancement? And this is why we ran a grid of models. This is coming from the star evolved models. And the zone you see here is a zone where you expect technetium-rich M stars, depending on the detection limits that I mentioned previously. So the technetium detection limit to classify this star as technetium-rich, and the zirconium to have zirconium band indices. Strong zirconium oxide bands. And you see the technetium zone is here, technetium-rich M stars is here. Okay, it's marginally matching the tracks, but it is possible to produce stars which show significant enhancements of technetium, but not yet that much zirconium. But so it is possible to have technetium-rich M stars, and it's not that odd that we detect them. So all of this and much more is wrapped up in a nice paper, which is now out, and you can find all of the details there. To just summarize a bit, comparing the spectral features of the S and the M stars, there's not much of a difference. The technetium, in terms of their technetium features, we did see a different sequence when we look at the TIO ZRO plane, which tells us that we need to think a bit about the classification schemes, but it doesn't matter, right? Whatever classification, S or M, whatever, what is important to take away is that M stars do show technetium and do show third Rejop features. So which means that whenever we are doing large population studies, we need to take into account that M stars can also contribute to AGB nucleosynthesis, etc. From the evolutionary point of view, where there's not much, we know that they are located beyond the onset of the third Rejop, and they have similar luminosities as the S-type stars. We also checked their spatial and kinematic properties, and we find actually there are several hints of these stars being a little older population than the technetium-rich S stars. So this is again interesting, older population and also low mass actually. So it goes back to saying that these are oxygen-rich stars with lower masses, maybe as low as 1 solar mass. So again, going back to the same thing that we do detect third dredge-up in low mass stars, and so on. So I invite you to actually read up the paper and yeah, to check for more details there. Something that still remains unanswered is, do these stars show other S process elements apart from technetium? And this question was very hard to attack from the optical spectrum because of the molecules, because it was a mess to find any atomic lines which could be really used for abundance analysis. And hence the title of the talk, which was multi-wavelength analysis. So we are expanding this study to an optical plus infrared combination, because you do need technetium, you do need optical for the technetium detection, but infrared can give you a lot of molecule-free windows to detect the atomic abundances, to derive the atomic abundances. And this is very much work in progress, but I'm very happy to share a teaser with you. There are several S process lines which could be useful. So this is for one of the stars which we are currently working on. There are some strontium lines and yttrium lines, etc., and several molecule-free windows. So we are very much excited and looking forward to really derive the abundances, to really see if they show other S process abundances, enrichment apart from the technetium that we have already detected. That is for my talk, but I would also like to make another announcement that the next the next Torino workshop will be a Solvay Torino workshop, which we are now planning in Brussels. It will happen in 2027 from 24 to 28 May. So, well, I look forward to, of course, seeing you all there, but I also hopefully will see you in 2026 as well at some point. But that's all then for my talk, and I'm open for questions. Thank you.
We have time for 1 or 2 questions. Question over here. So don't forget to introduce yourself. Thank you.
Yeah.
For the third time.
I'm Theo Kouri from Chalmers. Yeah, I'm introducing myself a lot. So when you show these indexes for the bands of zirconium oxide and titanium oxide,
If I can go back to my slides, yeah.
then I was thinking that maybe it's a metallicity thing, that if you have more TiO, then you have to dredge up more zirconium to then, for the bands of zirconium to become stronger. But then what you said later, that those stars seem to be from an older population, kind of doesn't really agree with that. Could you comment a bit on this?
It's a little bit messy. So first of all, we do not have the exact metallicity estimates because, as I mentioned, we couldn't do abundance analysis from the optical spectra. So this would be also something to check for later, to have actual metallicity determination from the observations itself. So the metallicity, the age, the mass, whatever I'm now talking about is coming more from a kinematical point of view. And of course, these models also have their own uncertainties, etc. Indeed, what we see from the TiO ZRO bands, what I also checked, if my slides can be put back. Can I have my slides again? Yeah, thank you. So we did, I don't know if it's part of this plot. Why is it not? But we did check alpha enhancement, for example. Yeah, so you see the 0.4 alpha enhancement, basically. So I ran spectral synthesis models for models enriched with alpha, and then hoping that, okay, that's the same effect on the oxygen, on the titanium as well, to see. But the bands, of course, they get affected. They get more affected by the macroturbulence, but this is all mostly a temperature effect here in this plane. So basically, stars moving top, shifting top at the higher, with a stronger ZRO band is a temperature effect. And it's really difficult to segregate all these different effects in just this plane, in just the TiO ZRO plane, basically. You have the temperature effect, you have a slight metallicity effect, as you see between the two sequences. This is a high mass, this is high metallicity and low metallicity. I think I'm going from solar to -1. So you basically manage to span the whole width on x-axis like that, because again, metallicity having an effect on the titanium oxide bands as well. So it's more complex. explain that. Yeah. Thank you.
I think we might move on in the interest of time, but if you have questions for any of the speakers of the sessions for today, don't forget you can post them on Slack as well. So I think we might move on to the last question. So thanks, Shreya. That was great.
Thank you.
So the last speaker for this session is Nicoletta Sanna, who is going to talk about the lithium-rich stars in globular clusters and what is their origin. Thank you. Please take it away.
Okay. They should arrive. Okay. Hello, everyone. I'm Nicoletta Sanna from INAF Arcetri, and I'll talk about lithium-rich stars in globular clusters. Let's see if it's work from here. Yes. Okay, as you know, lithium is a fragile element because it's destroyed at a low temperature. So it is preserved in dwarf, unevolved stars, and then it starts decreasing. And so lithium traces the evolution of stars. In fact, as you, I don't know if it's the pointer. Yes. I don't know if, okay. Looking at the main sequence stars, you can see that all the stars share the same lithium abundance. And then as soon as the stars exit from the main sequence, the abundance start decreasing. So until a plateau around an abundance of 1 after the end of the dredge up and before the bump, and then decrease again. So in principle, when you know the evolutionary stage of a star, you should know which is the lithium abundance that you expect. But there are some enrichment paths that can produce new lithium, so it can change the abundance of lithium in a star. And these are the three main mechanisms. The first one is the production of fresh lithium. That could be through the Cameron-Fowler mechanism, if the star is massive enough to have a temperature to do this, or some kind of extra mixing, especially for stars of low mass, like the stars in AGB in globular clusters. Or could be some kind of mass transfer in binary systems that could be a star, the companion, or engulfment of a substellar system. Or could be also the third path is the ejecta during a nova outburst of a companion star. But usually this scenario is not taken into account when you think on whole stars like globular clusters. Okay. Why this is important? Because we know that there are some stars, lithium-rich stars, that has a higher abundance of lithium respect to what expected. And here you can see the case of globular clusters, where this phenomenon is extremely rare because only 16 lithium-rich stars have been found so far. And you can see here a normal abundance of normal stars in the globular clusters, and here are the lithium-rich stars. So there are some stars that has a higher abundance of lithium, what expect, and some that are really, really extremely higher, the abundance. And one of these stars is this one, is the lithium-rich stars in NGC 1261. That we discovered using Gaia ESO survey data 5 years ago. For this star, we should expect an abundance of 1, while we found 3.4, so extremely higher. And we focus on 3 different lines to try to understand how can we explain this star. We focus, oh, sorry. This one, okay. We focus on lithium, where we compare the star with a normal star of the cluster with same parameters. And you can easily see that the lithium-rich has lithium, while the other, in practice, has no lithium. Then we focus on barium and H-alpha profiles. Here you can see that the barium between the lithium-rich and the normal star are almost the same, suggesting that the abundance is the same. So the two stars are two RGB stars. And then if you look at the H-alpha profile, you can see that they are extremely different. So we try to understand, to figure out how can we explain this. We test different scenarios. So we start with the scenario 1, that is the production of new lithium. And that could be because the star is at the bump of the red giant branch. So it could be that there's some kind of extra mixing that occurred. But then we cannot explain the difference in the H-alpha profile. So it's a possibility, but we are not completely sure. So we investigate the scenario 2, so the possibility of a mass transfer. We imagine the companion is another RGB star, and could be because the barium lines in our stars is the same, so nothing affected the barium abundance of our star. But that means that the RGB that accreted that is transferring mass to lithium-rich star should occur extra mixing to produce new lithium. So it's a possibility, but again, we are not completely sure and we cannot exclude this scenario. The possibility of an AGB companion that could explain why can easily produce lithium and transfer the lithium, but the barium in the stars is the same. So this means that should be an event quite a recent event. So again, possibility, but we cannot be sure about that. The engulfment of a planet could explain the different H-alpha profile, because could be some kind of activity in this star. But in that case, we would expect a higher value of lithium. So we conclude that we have some possibility, but we are not we cannot exclude any scenarios, but we cannot affirm that we know how we explain this star. So the conclusion was we need more data, and as usual. And so we realized that we need more data, but not only for that star, but for all the 16 lithium-rich stars, because we want also to understand if there is only one mechanism that can explain lithium-rich stars in globular cluster, or if more mechanism can be occur at the same time, or if it depends also on the evolutionary stage of the star. So we focus on the lithium-rich star of M3. This is a bright lithium-rich red giant branch star, and we are using JARPS data. JARPS is the simultaneous use of ARPS Nord and JANO, the two high-resolution spectrograph at Telescopio Nazionale Galileo in La Palma, and it allows to obtain the same time optical and near-infrared data, and so a wide spectral coverage. And we ask for this star multi-epochs to searching for a binarity signature. And this is very preliminary result. Here you can see the it's the same. Here you can see the comparison between the lithium-rich stars, the lithium line, and a normal star, so same parameters but no lithium. And here you can see again the comparison in the H-alpha profile, where you can see that the blue is the lithium-rich star. The profile is different between the normal star and the lithium-rich stars, but this is different in a different way from what we found in the other star. So in the other clusters. But for these stars, we have 10 epochs for the moment. And here you can see that the 10 lithium profiles are always the same. So lithium is not changing in the star, but the H-alpha profile is changing. So there is the blue wing that is changing a lot. And so we focus on the radial velocity Also because these instruments are, have high accuracy and high precision that can allow to determine accurate radial velocity. So we discover a radial velocity variation of about 0.9 kilometers per second in the star. And here you can see in blue the optical data, and in pink the near infrared data. And that has a very different signal to noise between this data. So the near infrared data, JANO data, have a lower signal to noise. But in any case, the difference that we obtain is almost the same. So this suggests that there could be a Keplerian motion instead of a stellar activity, because in case of stellar activity, we should find a difference in the radial velocity variation between optical and the near infrared. So we tried some statistical methods to investigate, to derive the information of binary, like the period, but we couldn't find any solution. Also because the accuracy of these instruments, if this data is so high that the error bars are included in the points. So in practice, we cannot explain how we can obtain this kind of variation, and could be a combination of more effect. We have no idea. I mean, we are still working on this. We still have to do the spectral, the chemical analysis to understand if there are some more difference between the profiles, the line profiles, not only the H alpha. But for the moment, it seems that the only lines that is changing is the H alpha. We ask for new data. We are waiting for them. Also to monitoring the normal star. Because what we realize is that we have no idea how is the behavior of a normal star, because there is no monitoring of normal red giant branch star. So to understand how this variation is due to normal activity of the star, that is in any case losing mass, so some kind of activity is expected. So we are waiting for new data. And in general, we want to investigate all the stars of the lithium-rich. There are only 16, so it's something that is doable if the telescope gives us time. Because the problem is that there is no systematically study on this and not homogeneously analyzed and observation. So for some stars, we have some spectral coverage. For others, we have others. And only for these stars, we have multi-epoch. So I leave you the conclusion. Thank you.
Questions? Oh, sorry. Flavia. And don't forget to say who you are.
Yeah, Flavia. Thank you, Nicoletta. But do you know if these stars comes from a first generation, second generation in globus clusters? Do you know if?
We don't know.
Ah, okay.
No.
I
mean, we don't know for the moment. We haven't checked with chemistry, because it's something that we want to know, but I think that is something that can, I mean, we know that in globular clusters that is the problem of also the problem of multi-population. So I don't know if knowing which is the population can give us a solution or more problem, but it's something that we are taking into account. We know that this is why, for example, for these stars, the star on M3, we select two normal stars as comparison, because looking just at the color magnitude diagram, we couldn't say which, if it was first or second generation. So we decided to, because we had just ground-based photometry, that it wasn't enough to understand the population. So we select two stars, saying maybe we found some difference and we can understand which is the population. So.
Okay, because if would like to believe in the AGB scenario, maybe you can, and if they are not first generation stars, could be a way, probably you can check. If you
Yeah,
can
absolutely.
explain.
Yeah, yeah. It's in the plan. Thank you.
Maybe one more question, including online. Of course, you can always pick up. Shreya, please.
Hello, I'm Shreya. I hope you remember me from the last talk. So my question actually was, you showed us the example of the lithium rich and lithium, no lithium star,
Yeah.
right? And there you're just comparing two stars, right?
Yes. Okay. This is the case of NGC
And these are two
1261.
stars. I was actually just curious if you have checked with the synthetic spectra. Like, I mean, could there be, because this is all based on one lithium line at 6,7,
Yeah.
right? And do we know what are like the blends in this line? So yeah, that was just my curiosity.
Okay, in this case, we have giraffe data, so the resolution is 20,000. And we check, and we can measure the lithium line, this line here, just the only one that we have. And this is what we obtain. But also looking at M3, where we have a HARPS-NOR data that is a higher resolution because it's more than 100,000. For the moment, we cannot see anything. I mean, it's what I show is what we can observe, but we haven't yet performed, and we haven't performed the synthetic spectra yet. So it's in the plan, but it's really, really new results, preliminary results. Thank you.
Right, I think we can end the session, but before we thank all the speakers, just a reminder that if you have any last-minute changes to your presentation, to please let the LOC know, because otherwise they may not know to upload the latest version of your PDF onto the talks. Okay. All right, so let's thank all the speakers of the session for the fantastic talk. Thank you. No, when do we come back, since we're running a few minutes late? I'll let you.
We come back in 30 minutes. 30. Yeah, it's just I have no idea what time is it now.
Okay. We'll need our...
Actually, no, we come back at 4, so in 20 minutes. Yes, but I didn't remember the program.
Hello, Julia. No.
One, two, three. Yes,
Yes.
yeah. Can you
I
hear
hear
us?
something?
Yes. In fact, we were talking to you since the beginning, but we realized that the microphone was not working properly. Sorry.
I was sitting here. Okay, but yours. Okay.
Yes. So could you maybe put full screen your presentation and we just look if everything is working on your side and move from slide to
Do you
slide?
see something?
Yes, we see your presentation without any issue. For now, you're not in full screen.
No, no,
We are
no.
seeing.
If I want to go around, I mean, and I don't have to go. So if that works,
Okay. If it works like this for you, we see the presentation like this. It's okay.
do you see my cursor?
Yes, we see your cursor too.
Oh,
Yes.
great. Yeah, I need that. So the
Okay. Okay.
oh,
So
super.
let's keep like this. Okay. So you're already all set up for the presentation. You are already displayed on the big screen. I mean, okay, everything is working. So no worries.
Yeah,
And
yeah, I can just switch to presentation mode.
yeah.
Okay, great.
It's in at 4 p.m. local time. Yeah. In
Yeah,
15
okay.
minutes. Okay.
Okay,
Super.
great.
Thank you.
I'm here. Go for food.
Se ve, dice, con la batería se le esquivó, ¿verdad? Ah, ¿verdad?
Good afternoon. Please take your seats. Welcome to the last session, the last talk session of the day. My name is Xavier Bois. I am from ESO Chile. I will be chairing that session. And we will start with an invited talk by Bernd Freitag, who is online. And he will tell us about 3D simulations of the dynamics of life of the atmosphere and the wind of AGB stars. Bernd, if you can hear us.
Yeah, okay.
Yeah, feel free to take it away.
Hello, everybody. I'm working within the X-Wings group, where we perform radiation hydrodynamic simulations of the outer layers of AGB-type stars and red supergiants. So the core where nuclear processes happen that we heard about in the previous talks is far below what we can resolve. If you want to go to a different stage in the stellar evolution, we need different stellar parameters, different equation of state and opacity. So we don't follow evolutionary changes, but we take a given state and then try to model dynamical processes that happen rather rapidly. We use 1D Darwin code and the 3D Cobalt code. One side of our work is to produce observables, compare with observations. And then with the simulations and what we learn from observations, we try to understand the physics of the atmosphere, particularly the mass loss process. And our final goal is to quantify the mass loss rate for all possible stellar parameters. I will talk a bit about dust and how the dust clouds look like, but after me there's Joachim Wiegert, who will show you how these things actually look like and some observational examples. So I will rather concentrate on the physics behind the reason why we don't have spherical mass shells moving out, but clumpy clouds. I present first the code very rapidly. It has two geometrical setups. One, local, where we simulate typical small-scale patches on stars like the sun, other main sequence stars. I will talk more about our global simulations, where we have the entire star in the box, and where we can even include star and wind formation region in larger scale simulations. The solar type simulations are mentioned here because this is sort of the basis of the entire research field. Lots of code can do this. We can compare codes. We can compare them with observations. Here on the top, it works very nicely. And we use that sort of this confidence. Then we go to related stars, main sequence stars, with more and more differing stellar parameters. But the further we go, the more different convection looks like. And I'll try to argue why AGB stars are really different animals than just blown up suns or main sequence stars. So we have, I will talk about hydrodynamic simulations, compressible, so we account for shocks, ionization, gravity is a simple potential. Most of the computational time goes into solving the equation of radiation transport. Because the radiative time step is so small, and we have modules to include dust, optional. I will talk about a module that counts for the source and sink terms of amorphous magnesium silicate. It would be forsterite if it wouldn't be amorphous. We have interaction with radiation, so we can drive a wind simulations. I start with the sun because it's often still use as the example for granules that exist everywhere, just scaled up. On the sun, we have this is a simulation, old one. We have this pattern of granules. Here's one, another one, so 1,000 and a bit kilometers in size. So it's about 10 surface pressure scale heights or so, where we have bright material coming up, cools down, moves to the side, and then sinks down into dark intergranular lanes. A slide, sort of taken here, but now with the height coordinate and the horizontal coordinate as before, shows this downdraft. So this one, the entropy. So we have dark, cool material going down. It's nicely turbulent. And not in this example, but often the downdrafts go very deep. But because in the sun, the density and the temperature, the internal energy increase so rapidly, the velocities go down very rapidly. So essentially granulation is formed at the surface. We don't need the deeper layers really. In addition to the granules, we have waves, they have a tiny amplitude in the atmosphere, but they move up, transform into shocks in the upper layers. So now the sun, to a few examples of stars from 8 solar masses computed with this global setup. We see possibly here some kind of surface granules. I mean, there's something small on the surface, but most prominent are these dark patches hovering above the surface. If you analyze it in detail here, perhaps you can see it towards the limb. It's just slightly above. And it's cool, dense material where molecular opacities get so high that they block the light from below. Now I try to analyze how these things come from, because they play a role for the formation of dust later on. So first I look at the granules. So I take a star, say, on the asymptotic giant branch, but rather low. So not a Mira. This is the model perhaps closest to a solar model because it's almost spherical. There's small scale stuff on the surface, shouldn't have a wind. And we look at the surface. So this is not an image taken out, but it's actually the temperature to the fourth power at resonant depth of unity. So it's very close to the image. You just don't see any limb darkening, you would see. And you have structures, but it doesn't look like solar granules. But I can make them visible if I look slightly deeper. So I could use a larger tau Rosalind, rather optical depth at which I render the things. On the right, I take radial velocity at 7,000 Kelvin. So it's slightly below the visible layers. No? Effective temperature is around 3,500 Kelvin. So up slightly below the surface. The star is only a tiny bit smaller. And then I render the outflowing material blue, so towards the observer sort of, or radially out, and red material going down. If I would have chosen the black-white color scale, it would have looked like granules. So the granules are there, but below the surface. Because the opacities are so that there's too much material above, and with the high opacities, I don't see this common pattern. If I look further in, so 25,000 Kelvin, I still see downdrafts, sort of convection cells, but on much larger scales. And because flux per area increases, and so there's more energy transport through a given surface, the velocities don't decrease as much. So the interior layers matter much more for the surface than for the sun, and in the solar case. So this is sort of this is one star, and I want to analyze the granule size systematically, and I do this for a number of models and compute spherical harmonics, so slow Fourier transform, and then plot it over the angular degree. First on the right, I do it for the radial velocity. So in principle, the thing I displayed before. And then I'd also do it for the temperature. Now I have temperature isosurface of 7,000 Kelvin, but then one step is to sort of smooth the surface. So the downdrafts, the isotherms go a bit inside the star. I fill that up, and then I have a temperature map on the surface. Oops, sorry, oh, that was too much. Low luminosity model here, okay, it's the largest angular degree, and then things get larger if I increase the luminosity for these two cases. But, I mean, this was sort of my first idea to do this with, again, sorry. It's, okay, with the radial velocity. But you see, there's not just a maximum for the granules, but there is something on large scales. So to account for the change in surface gravity, and so I scale and this angular degree, so that in this case it's kind of frequency. I mean, it's still angular degree, but scaled, so that say 0.06 would correspond to 16 pressure scale heights per wavelength. I mean, wavelength in 2 dimensions on the surface. So it's a bit of arbitrary factor and so, but in principle, it's a frequency. So 10 pressure scale heights per granule would be here, 20 here. And so the models are better normalized. And I see, I mean, indicate the maxima here, and the temperature plot for the granules. That is a trend, but typically they go pretty well with the scale height. If you compare the previous, we had a large trend, and this one, well, it's constant. But what's obvious are these peaks here. So this is, I mean, 0, the radial sort of doesn't count, but then the first we have a dipole mode here, and then sometimes sorry, you have to look at the non-scale. So here the dipole, here the quadrupole, they mess things up. So the deeper layers, the global convective cells that are to some degree driven by the potential close to the core, shows up at the surface. So now these are layers close to the surface, and they mix for the top luminosity AGB type stars. So the granular size, perhaps the granular size would have this trend, but it really goes this way because there are the large scale flows influencing things, and they have actually large power. So if you look at the largest luminosity for this one solar mass sequence, so it's always one solar mass in this example. So the things are difficult to disentangle. What really plays more role? I mean, a stronger role, the deep cells or the surface cells. So we have granules that play a role and the longer lasting deeper cells. Next, I do a look at the, not light curves, but at spectra in time. I mean, time sequences that are Fourier analyzed. We have seen period luminosity diagrams before. This is a sequence of models, the same I showed before. One solar mass models. Each horizontal line is one spectrum. So 800 solar luminosities to roughly 10,000. And what I analyze here is the added power of 6 intensities. My computation domain is a box, so I get light in 6 directions, compute the power spectra for the 6 directions, and add it up just to get better statistics. I mean, I have the data, it's cheaper than computing 6 times longer a sequence. So it's sort of unobservable, but to connect things here is a bit difficult. So I broaden the lines and apply an arbitrary slant, sort of to make things fit. So it's sort of roughly 1, it's a constant. It's a bit artificial, but just, I mean, it's the same data as here, but to connect these things, I reduce the slump. And we can see nicely here, so it's an arbitrary scaling of the color. Can see here largest amplitude, likely the Miras, so 6,000, 7,000 something solar luminosity, so far away. And then we have these ridges. It will, as it turns out, there's a different radial orders, and then we have some substructure and quite some power around. So there's also power here, but it doesn't form any ridge. So there's no sign of a long secondary period, even if there are physical processes that produce longer time scale phenomena like ballistic motions in the atmosphere or the change of convective structures in the interior. So they give power here, but they don't give a period, unlike the pressure waves that give the ridges. And I try to analyze the ridges. To analyze this a bit, so I have a number of pictures looking very similar. Here, almost the same thing, but it's now looking at the surface velocities. We compute spherical averages during the simulations, and not only spherical averages of the diverse quantities, but also averages weighted with factors, so we get the spherical harmonics. And then I average the data for the first 4 modes. So it gives essentially the same. I go back, intensities, velocities, essentially the same. I mean, subtle differences. But the trick is now that I can do it for a single mode. This is the radial mode only. Okay, as expected, our Mira candidate objects have the largest power. I mean, by far. If you go down luminosity, power goes down, it doesn't vanish, but the maximum switches to the next branch. So from N0, so purely radial fundamental mode, to the first overtone in radial order, and perhaps here the maximum at the coolest model is on the N equals 2 branch, and there's perhaps another more. When I go to the dipole mode, it has a bit longer periods. Has a maximum at the N equals 1 branch, and it's much weaker, so therefore the background gets brighter. So the plots are scaled individually to make it look good. So I can do this. So this is the dipole mode, L equals 1. I go to the quadrupole mode, has a bit higher frequency, but lower period. And I go to the L3 mode. That almost coincides with the L in frequency here, with the L equals with the radial mode. And I think, so I go back to this. So here we have a Mira type pulsation. So it's the interaction with the convection doing it. In the bottom layers, lowest luminosities. We have lots of modes. So I like to think of this as a blown up sun really at 800 solar luminosities. So lots of modes where the power is distributed over several modes without any clear mode with the highest power. So now I go back, I can do a similar trick for the intensities. What I do now is add the intensity from the 6 directions. So that would require 6 satellites placed around the star in the 6 directions, but I can add them. I mean, in the models, I can easily do this and can extract the fundamental, the L equals 0 mode, radial mode. If I add clever weights, so taking the intensity towards the observer, intensity minus the observer in the other direction, ignore the others, I can extract the dipole mode and the L equals 2 mode. So this is just a decomposition of the actually observable thing. So, but it shows that I can actually see, should be able to see the modes in observables. I mean, this decomposition is a mean trick by theoreticians, but it should be observable. So another thing, if you look at the modes, you get 3, for instance. So I go back to the velocities, I have a peak somewhere of the mode. It gets, rather sharp, decreases in amplitude with the lower luminosities, but when I go to higher, it doesn't actually vanish or so, but it gets broader. And one could argue that, depending on how brave you are, but you see it pretty high up. It's slightly embarrassing because some time ago we wrote we couldn't see other modes. I go back to the Mara stuff, so we have the Mara mode. We didn't see, we saw some signal there, but interpreted as noise, something that's not a mode. But if you make this, look at these types of plots and see, there is actually power that still corresponds to the next higher mode. Those are the much lower power and much more spread out. So it's hard to pin it down. You have just a broad band of small amplitude peaks there. But we claim there are modes. So even if the Mara pulsation is essentially radial modes, there is this tiny contribution from the other modes that kill the exact spherical symmetry. So I have the mode, I have to go forward. You've seen this. These were the modes. Now, so we had the convection, having small and large scales, destroying the spherical symmetry, and also the modes show we have the radial mode, that's perfectly spherical symmetric, but the others contribute even in the sort of Mira regime and destroy the perfect symmetry. And I show this image again. So this were sort of the underlying physics. Now, so we have now fluctuating flows, fluctuating convection, fluctuating pulsations that shift and push material in layers on top of the convection zone. And we can get a rapid cooling. Molecules form, the material gets pretty opaque, gets very dark locally. There are different dynamical processes that show this. We have written a paper about this. I will not go into these dates, but because we're out of time, I have to go now to the dust part. This is a model where the star is this tiny blob in the center, and we have much larger box, a few thousand stellar solar radii, where we see shocks, blue material moving out, outward moving material here, form of shocks, and then behind the shocks, material falls back towards the star in red. Now I want to concentrate on this shock here, going here, because the dust forms, growth and extension. It's a bit, it has a structure, but it's about what we think, what happens in 1D models. So these are slices of the models. I want to look at it in a different way. I'd compute histograms. So for each of the 5 snapshots, I show histograms on this plot and the coming 4. I have 2 models now. One with efficient dust formation. So it's the sticking coefficient. Whenever a molecule, the right kind, hits a dust grain and the temperature is right, it sticks and makes the grain grow. There's also a case where the sticking probability is very low. So most of the molecules just are reflected or something like this. As a kind of embracing the uncertainty we have in our dust model. Perhaps, we are more certain that's a larger value, but just as these contrasting cases, it might be interesting to analyze. I will look at the structure here and here. The dust forms close to the star. So the histogram, so we have radius and radial velocity as data here. Brighter means there are more grid points with that velocity, and blue means dust is forming. So I go forward, so follow these blobs here and here, further out. Here you see the velocity pattern looks with or without dust is similar here. There's enough dust so that radiation pressure on dust accelerates the material. So it goes up and the velocity histogram moves out, and we get the layers here. Actually, with the model with strong dust formation, the velocities kind of stay above zero, so the orange line. And the model here has material moving out and then material falling back. The average over time is still, there's still a net mass outflow. Turns out if I remove the dust completely from the model, compute the sequence, there's also wind. So there can be small wind without any dust or with very inefficient dust formation, but to get the high mass loss rates we expect for Myra type, well, we measure, see, and deduce from the material outside, we need the formation of dust and the additional pushing by radiation pressure on dust. So that's my last slide. I try to introduce you a bit to the dynamic of phenomena at rather high Mach numbers that contribute to the dynamics, produce small and large convection cells, waves of different wavelengths transforming into shocks, which are actually sufficient to drive a weak wind. But we need dust and radiation transport on dust to get realistic Myra type stellar winds. Thank you for listening.
Thank you, Bernd. We have time for a few questions. If you have any, please start by introducing yourself, as usual. I can see you, Theo. You have a question? I'm here.
Okay.
Hi, Theo Koeri from Chalmers. Hi, Bernd. Very nice presentation. So I was wondering, now in the end, when you said that you can get outflows even if dust forms very inefficiently, I think that's very interesting. Can you quantify that a bit? What level of mass loss rate can you get in this type of models?
Joachim will do that. He has a table, so I omitted it. Sorry.
Okay,
but it's more so 10 to the -7 something.
Okay.
Something in the next talk. Sorry. And it only works for, 7,000 solar luminosity is pretty high already. If you go a bit lower, I don't have all the models that's completed, but the models I have are mostly just star in the box. We have only a few models, including the wind region. It's much more expensive to compute, but it will stall at some point. But the density drops so much, even if some material goes out, there is just hardly any material at the outer layers of the box. So we need rather high luminosities to make that work, and we think dust works and even in more difficult cases. But this is still on the to-do list to make a larger grid and to compute mass loss rates for different assumptions. And so it will hopefully come, but it's not there yet.
Lynn, I think you're the next one.
Hey Bert, Lynn Desin from Leuven University. I have two questions. The first one is just a technical one. In all of your plots where we did see this pure luminosity values, there were horizontal stripes. What is the cause of that?
No, that is, I try so each stripe is one model, and then I blurred it they can blur it more, then you don't see the stripes. But I thought it's kind of honest to keep the stripes. So this is a bit complicated, a bit engineered. So it took me a while to make it, but it's, yeah, but the stripe, this is just one model and another. I don't have 1,000 or 10,000 stars.
Oh,
The observers have in the Ogle maps. So, but
yeah. Going now also to the stars, is there any comparison you can make with observational data?
in
Since
what
you have predictables now,
in the paper by Arif Ahmad et al., also do comparisons to observed periods, so from this type of plots.
Yeah.
In the next talk, Joachim will tell about what can be done for the dust clouds, could be done.
Yeah. But no, I was more
one problem is that the observers come with a mass of a star plus minus 50% or so.
Absolutely.
And that changes things dramatically in the model. So we have an enormous large error bar that so we can excuse things. If some things don't work perfectly, then we say, the mass of the object is that we assumed is wrong. So but there have been comparisons by Andrea Chiavassa, but more it's supergiant. So we qualitatively it looks okay, but for real quantitative comparisons, we need actually better stellar parameters. So we can say, this model compares to that observed star, and we don't have that. It's kind of weird statistics we have. So I think it's good, but it's not honest.
Yeah, it's really good, but I see what you say. Okay, thanks.
We have time for the last quick question. Yes.
Shazreen Mohammed from University of Virginia. Thanks, Bernd, for the nice talk. You mentioned the long secondary periods and that there was a little bit of power there. Is it that you don't see it because it's not really there? It doesn't form a ridge, or do the models need to run longer in order for you to get more power in that?
I don't think the models need to run longer. So they are actually, these models are there. Rather small, so not the wind, not supergiant, so it's kind of rather cheap. So we couldn't afford a number of them. We have actually models for 0.8 and 0.7 solar masses. So we have started working on a grid. So, and I actually ran the models for quite some time and made a plot here so wide. Actually, you see kind of the signal ends here, but I added this region in the plot to see if there's something happening. So we have 50, 60 normal pulsation periods, and then if it's a factor of 5 or 6 or something longer, we should begin to see something here. I don't think it's the length of the period. So it's so that the power is there. I mean, things are happening on these timescales, but they don't form. I mean, there's nothing happening at a certain factor times the normal. That certain factor times the period of the fundamental mode. So it's just distributed over a large range.
Super, thank you.
Thank you very much. Let's thank Bernd again, please. And now we move on. We have Joachim Wiegert, who will tell us about time-dependent synthetic observables of 3D AGB star and wind in a box models. Please take it away.
It works. Okay. There. So so Bernd has already introduced X-Wings project, so I will not stay on that topic too long. But in short, we are interested in simulating the interior, surface, and exterior, and the surroundings of AGB stars in 3D models, and we have several publications already, and for me, I showed two here that are relevant for this project that I'm talking about. And the first one here is the first one that includes the simulations with the larger computational box that also includes dust formation and the initiation of wind around these stars. This is my first publication in the project, where I present my methods and how some results on one snapshot of one model. And this draft here is what I will be talking about here in this talk. So yeah, we already heard about cobalt. We use this. It's a 3D radiation hydrodynamical simulator to simulate AGB stars and the initiation of wind. And I take those data and translate them to RADMC 3D for radiative transfer simulations. Including the dust around the star, and the aims are to relate our models to observations, what can be observed really, what predictions are observable, and I'm interested in the dust around the stars that are important for the wind to start. We see a lot of dust around our models. Is this too much? We want to test our models at this. So I'm working on trying to figure out some statistics on how that could be used for planning observations, that is. And I touched this here with we're not sure how exact the dust model is, so how we want more insights on our simulation parameters. So I'm working on 3 different models. I could name just A, B, and C. The model A is already published several times, and Bernd mentioned this as well. But all 3 models have similar stars, one solar mass oxygen-rich AGB star. The dust we're forming is phosphorite-like, and I use data from the IU GENA database for opacity data. I include some 60 to 70 years of simulation time on each model, and the primary difference is, of course, that we change the sticking coefficient to change how much dust is formed around the stars. So A has 1, and B has 1.1, and C has 0.01. The approximate mass loss rates, so you can have something to relate to, is 5 to 0.1, 10 to the minus 6 solar masses per year for each of these models, A, B, and C. The image on the right is just to show what the data looks like before the radiative transfer computations are done. So that's similar as Bernd showed earlier, what's called cut-throughs. Look through the middle of the computation box. So you have the star in the middle. So this is the gas densities seen from 2 different directions, and the gas temperatures and the grain sizes, which maxes at 1 micron. Yes, so some images. So I simulate mostly images of these models. These are at 10 micron because I want to look at the dust emission of the most dust-rich model. You can see this is quite dramatic. There's lots of things going on around this star. You have the hot gas and star in the middle here. The star has a diameter of 3 astronomical units, and the computation box has a side of 30 astronomical units, so it's like 1/10 of the side, approximately. So yeah, lots of dust forming. Some is more spread out, some is much thicker and blocking the star. Sometimes it's like these shells that fly away, and sometimes it's destroyed. A lot of things going on. In the B model, much less dramatic, but still lots of things going on here. Sometimes it's almost no dust around at all, and sometimes it's just very small, faint cirrus features, thicker dust clouds around here as well. And in the C model, of course, even less dramatic, but still some clouds are forming. Mostly the C model is like more similar to our dust-free models. So these are just, so in these 3 cases, these 10 images I've been showing is just 10 random images of more than 400 snapshots for each of the models, and looking at 6 different directions. I forgot to mention this, that I simulate images in 6 orthogonal directions, because I want to see the model in all primary directions. So I can show all of those images, of course, but I can go into statistics, and looking in more globally, I can look at the total dust mass in the box for each snapshot. So I get like a time evolution of the dust mass in the box. And the A model is, well, of course, much more dramatic. It's a blue curve here, while the red curve is the B model. But in average, they are quite similar. The dust mass, average dust mass is just a few, a factor of a few different, while the C model has an order of magnitude lower dust mass. The gray box is where the dust production is not relaxed. So you see the C model has a very decreasing dust mass there. It's not included for the average numbers. So we have, well, dramatic local differences. That's dust formed near the star, destroyed, formed because the temperature changes so quickly on the stellar surface, and then you have lots of dust forming, which is then immediately destroyed because the temperature increases again. So that's one thing that can happen, while the slow changes is more related to the mass loss rate of the star. We form the dust that survives forms a wind and is blown away, and it slowly decreases the dust mass around the star. What's interesting here is the Ducey model is mostly has not much of the dust-driven winds, except in it's more like a puff behavior, that you have localized formation of dust around the star. You can get these thick clouds, like I showed here, that you have sometimes these clouds forming, but might be destroyed. Sometimes they are blown away. So even though the C model has, in a way, too little dust formation to actually sustain a dust-driven wind, it happens, but during short time scale, during just localized directions, and not for a very long time. But still, even though you have a low mass loss rate, you can have some dust-driven winds according to the model, but it's of course difficult to observe, because when do you catch it? That's the question here, how to observe these events, when the dust clouds form. So I try to do some statistics on this. These are histograms of the size of the dust clouds in all the images, in all the 6 directions for the 3 different models. I identify dust clouds by limiting the flux density, looking at flux density higher than some decided by the contrast to the star. So the flux density from the dust pixels in the images must be higher than 1% of the stellar flux, or a bit hand wavy. Maybe I want to have some kind of how deep can you actually observe? So for 10 micron and be able to resolve the dust clouds around the star, you need something like VLTI and the Matisse instrument. So that's my inspiration. So something like 30 minutes might be a reasonable exposure time. I'm looking at Claudia. She's anyway, that gives me a flux density on how deep I can watch, and 200 parsec to the models, that is. And I look in the region where the dust and the wind is formed, is starting, and that's between 2 and 6 stellar radii from the centrum of the image. And finally, for the more large-scale statistics, I divide up the clouds in ranges of size depending on the stellar area in the image with a constant radius 1.65 AU, and look at everything that's larger than that to get some numbers. So these are rather rough numbers. It's difficult to analyze this because it's very sporadic, the dust formation and the cloud formation. You can have lots of dust forming in a short time and then nothing for more than 10 years in some cases, and sometimes you have very irregular. But in general, in the best case scenario, considering snapshots and images where there is at least one cloud that fulfills my limits, in best case scenario, we have something like 2 to 6 year periods average. Like I said, it can be rather sporadic, makes observations more difficult. The clouds last almost 1 year, regardless of which model it is. And this probability I'm writing here is like the probability of catching the star in the act of having these dust clouds around. Some 15–40% probability for that. There's the number of snapshots with dust cloud divided by the number of snapshots totally. So it's rather simple. So how is this relevant? Well, there's already observations around, and I'm hearing there's lots more coming. So this is from Leah Plankert's paper from 24. Of course, this is a carbon-rich star, carbon dust. So I'm cheating a little bit. Carbon dust is much more optically fixed, so it's more simple to get heavy effects. And this is Myra scattering on dust at 0.65 and 0.82 micron, VLTI single telescope. Similar shapes, similar size scale as our computation cube. These clouds are within 10 to 20 astronomical units from the star. So in summary, I'm out of time soon. We have simulated a lot of snapshots for 3 models. I try to compare them with the observations, but this is ongoing work. So these are ranges of mid-infrared colors of some almost 10,000 AGB stars, while my ranges are instead because of time in the simulations. But we are in the same ballpark, even with the most dust-rich models. So yeah, the numbers are already mentioned. So I'm looking more into doing some kind of non-general statistics. Is what's going on now, and further in the future, I want to compare more with large data sets, find maybe sources that exhibit similar behavior as our models, if our models are correct. That is, try to constrain our models better with observations. But thank you.
Okay, we have time for at least one question. Maybe online. Please, Theo.
Hi. So that's really cool. And it's really nice to see how the simulations are so close to what we can also observe now, as I will say much more. But I was wondering, when you talked about these dust masses in your box, have you guys compared those to the gas masses? Because I imagine that the dust to gas ratio varies a lot if you are in one of these clouds or not. So how does that compare?
Short answer is I don't know. I don't remember how the gas to dust ratios are in these models now. Does the sun, I may remember? No. Sorry, but yeah, sometimes I try to do some estimates, but then I just assume 1,000 as a dust to gas ratio.
But I was also specifically thinking, the difference between A and B? Is it so small because in the A you run into like a lack of metals at some point for forming more dust, or?
Sorry, but I'm running, what did you say?
That you form as much dust as you can basically in these clumps, or?
I don't think I understand the question, sorry.
Well, I would expect the A model, I think the point you're making is that the A model should have a lot more. It's surprising that it doesn't have a lot more dust since it has a C coefficient 10 times larger. And I was wondering if it is because the C coefficient is so high that you basically form all the dust you can.
Yeah, that's a possibility. I mean, we have these thick clouds forming all the time and then destroyed rather quickly or very quickly blown away. That would be an explanation, because the mass loss rate between these two models is not the difference, the ratio between them is not that high either. I mean, it's just a factor of U also.
Okay, thank you very much. I think we can thank Joachim again. And now for the last contributed talk of the day, we welcome Keiichi Onaka, who will tell us about high-resolution view of the atmosphere of the AGB star W Hydra with ALMA, VLT sphere, and VLTI Matisse. When you want, Keiichi.
Okay, yeah, thank you very much. So I'm going to talk about high resolution view of the atmosphere of the Hydra done with ALMA, VLT sphere, and Matisse. And here are my collaborators. Got that one at the Uppsala University, sitting there, and Gert Weigert and Karl-Heinz Hoffmann at the Max Planck Institute for Radio Astronomy in Bonn. So before talking about the high resolution view of the target, I would like to start from a low resolution imaging of our target. So this is a photo I took on Paranal several years ago, and the target is here. So I make a blow up. So this tiny red speck is our target W Hydra. And now a very quick introduction about the mass loss at the AGB phase, which is an important factor which affect the stellar evolution as well as chemical evolution of galaxies, because the up to 80% of the initial mass is returned to the interstellar medium, enriching with the different elements. And in the recent years, we have seen tremendous advances in the observational and theoretical understanding of AGB mass loss. Nevertheless, we haven't yet understood fully how the dust forms from molecular gas and the interplay among shocks created by pulsation and/or convection and dust formation, which finally leads to mass loss. And to tackle this long-standing problem, we need to spatially resolve the region within 10 stellar radii, and where pulsation, convection, and dust formation take place mutually coupled. And now it is possible thanks to the advances in the high-resolution technology. And our target W Hydra is one of the best studied AGB stars thanks to its proximity at 98 parsecs and its angular diameter of 40 to 50 milliarcseconds as measured in the near infrared. Makes it a very ideal target to spatially resolve its surface and the atmosphere. And this is a light curve collected, the light curve of W Hydra collected from ESO data, and it shows the clear periodicity. And I'm going to present the data observations taken here at the minimum light. First of all, our observation took place in band 6 from 251 to 269 gigahertz with a maximum baseline of 16 kilometers, which gave us a resolution of 16 to 20 milliarcseconds. As I show you in a minute, the millimeter continuum angular diameter is 60 milliarcseconds, so we can really resolve the stellar surface and atmosphere. And in our data, we identified 57 lines, which include the different isotopologues of SIO, vibration excited water, many SO2 lines, and it's isotopolog, SO, HCN, LO, LOH, TiO, TiO2, and OH. So I would like to go through the images taken seen in different molecular lines, some representative lines, because I don't have time to show all 57 lines. So this is the, we start from the high excitation 29 SiO line. So what's shown here is, oops, sorry. Oops, no. Yep. So this is the continuum subtracted map obtained at the systemic velocity. So this bluish circle, this corresponds to the continuum millimeter continuum size, 60 milliarc seconds across, and this is the beam size, so we can resolve the surface. And here over the stellar disk, we see the molecular line in absorption, because this is a continuum subtracted map. And you might be able to see that the absorption is not homogeneous over the stellar disk, but in this case, probably it's hard to see, but it's stronger in the southern hemisphere. On the other hand, the outside the stellar limb, we see the emission. So this is exactly what we expect from the thermal excitation. And okay, so I'm going to show you some representative lines, and the complete result will be published in ANA in 2 weeks, accompanied by a press release from ALMA. And now another SiO line, we see a little more emission. And this is a low excitation SiO line, and we can see the plume going to north-northwest, and the extended elongated atmosphere, and something is also sticking out to the south, like a tail. And another low excitation line shows similar structures. This is very different because this is strong masers. What's interesting is we see emission over the stellar disk, although this is an image after continuum subtraction. And this is a vibrational excited line, a water vapor line, and another water line. What's remarkable is the emission is covering over the stellar disk, although this is again a continuum subtracted image. So we detected some the emission, extra emission over the continuum, and as I show you later, we think this is a likely major emission. And the SO2, so the very complicated structures, clumpy and irregularly shaped, and the absorption over the stellar disk. But this SO2 line shows the emission covering nearly half of the stellar disk, again, although this is after the continuum subtraction. Another SO2 line covering partially the stellar disk, but in a different region. Again, the emission over the stellar disk. And this is an SO line, which is much more extended than other lines, more extended than 100 milliarc seconds. HCN line, very optically thick, so it looks very extended. But this one, this HCN is a vibration excited line. So we can see that, oops, sorry. The HCN is forming close to the star. LO, this one also shows slightly weak emission over the stellar disk. On the other hand, LOH shows spotty emission. TiO2, oh no, this is TiO. And then TiO2, rather noisy, but there is something. And OH. So actually, a third of the detected line shows emission over the stellar disk, which include SiO, water vapor, SO2, and LO. And we think this is non-thermal emission over the stellar disk. This means that it is superthermal or major activities. We don't think this is due to hot gas in front of the star, because in that case, we expect emission in all lines, which is not the case. So now we take a closer look at this line, water vapor line, okay. And if we go through the red channel maps, and now here we see absorption over the stellar disk, but at these the redshifted velocities, we can see the emission covering the stellar surface, and also very strong spotty emission. And this emission is twice as strong as the continuum intensity. So that's why we think this is a major emission. And because this is a thing at the redshift velocities, we think we see the info in front of the star. And now the condition for this water line to measure is cold and dense gas. For example, the water molecule density higher than this and kinetic temperature lower than 1000 Kelvin. And these are exactly conditions for dust formation to take place. So that's why we compare the measure map to the dust formation map. Fortunately, there are archival data taken just 9 days before our observation with a sphere simple instrument with a comparable spatial resolution. And now we compare this water measure map. And this is the polarized intensity map extracted from the program led by archival data of the program led by Theo. And we can see the dust cloud formation here, here, here. And if I overlay the measure emission, they agree quite well. So this means that both water measures and dust form in cool dense pockets, and dust is forming in inflow. We also compare the molecular emission with dust formation. For example, this is ALO, and this is the molecular emission. Again, this is the polarized intensity that reflects dust formation. And if I overlay the ALO emission, then again, they show very good agreement. This suggests enhanced ALO leads to enhanced dust formation. And we compared the dust formation map with the different molecular lines, and we find good agreement for SiO, SO2, and SO and TiO2. But this suggests that those molecules and dust form behind shock fronts, but not all molecules participate in dust formation. For example, HCN shows the emission, but if we compare this, the HCN emission and it's hard to see, but the contours shown in the dust cloud formation, HCN is forming close to the star by shock-induced chemistry, but the HCN is going beyond the dust formation map. So HCN is not taking part in the dust formation. So now we also obtained the contemporaneous VLTI Matisse data near 4 micron, and this is one of the SIO lines obtained with ALMA. And here comes the Matisse map obtained at 3.98 micron, which covers the H2O band. And then if we compare this, the ALMA, and this, then we are probing the region just inside the millimeter continuum region. And we can see that the stellar disk and the irregular extended atmosphere. And this is the 4 micron region image, 4 micron image with H2O and the SIO. And the atmosphere is more extended. And by the way, the beam size is 3 milliarc seconds. So this tiny white circle is the beam size of the our Matisse observation. But I need to stress that these are preliminary images, and we still need to check the fidelity of the image reconstruction. But obviously, we can probe the region inside the millimeter continuum with Matisse. So now, okay, so just quickly the summary. In many lines, we detected a non-thermal emission over the stellar disk, superthermal or major activity in some cases. And although we didn't have time to talk about kinematics, in our paper, we did do the analysis of kinematic, which shows and then we find outflow in deep layers within 2 stellar radii. But then above that, we found inflow above 2 stellar radii, which turns to outflow at larger radii, larger than 4 or 5 stellar radii. What we can do from the sphere data is we can constrain grain size, and from the Matisse interferometric imaging, we can constrain the density and temperature of the molecular gas, especially H2O and SiO. So with these multi-instrument or multi-facility campaign, we hope to get a more comprehensive picture of what's going on in the innermost key region around this star. Then thank you very much for your attention.
Any questions? Yes, please.
Hi, Elvire de Beck from Chalmers. I was wondering about your, oh, by the way, awesome data. Like, all over the place. It's amazing. But I had a question about the SO2. So you say that it might be maser action. Do we have any like constraints on what parameters or on what part of parameter space we would be probing there? I mean, for the H2O masers, you have some conditions there, right? Do we have that for SO2?
No, as far as I know, no.
Because I think I see that in, for NML-SIG, I also have some weird behavior with absorption in some lines, whereas others show emission.
Right,
So it would be very good
Yeah.
if someone in the room knows anything about
Yeah.
SO2 masers, then please.
Yes, please. That would be the last one.
Javier Alcolea from the OAN. You show these wonderful images with ALMA, but you never show us the continuing image. How does it look like? I just wonder.
It looks quite boring. I have a backup slide. Sorry, I have to go to the end. Yeah, this is the continua obtained at 268 gigahertz. It looks round, and then we detect a very, very slight asymmetry, but intensity contrast smaller than 1%.
Curious. So flat, I would say. No?
Yeah, maybe, but it's very, very weak.
Okay, thank you very much. I think we can thank Keiichi for his talk and all the speakers of today's last session. And now we move on to the next part. Martina?
Yeah, hi everyone, I'm Martina and I will be chairing the Flash Talk poster session. So before starting, I have a few announcements very rapidly. Presenters of tomorrow's session and Flash Talk, please remember to update upload the presentations in the folder. When leaving CEPAL after the welcome reception, please remember to leave the CEPAL badge. And tomorrow, try to come a bit earlier because we have to do the whole process again to get the badge to enter. So we can start at 9. Okay, so we can move on to the Flash Talks. I remember you that you have maximum 2 minutes, otherwise no welcome reception. I'm joking. If you have the microphone, you can just unmute yourself and talk. If you don't have the microphone, please raise your hand and I will come and give you give it to you. Okay, we can start with Miura.
Can you hear me? Hi, I'm Miura Angianzaralas. I'm a postdoc at Chalmers University of Technology in Sweden, and my poster is on the DEFSTAR project. So DEFSTAR, stands for Determining Accurate Muscle Rates for Thermally Processed AGB stars. And in this poster, we are presenting the results that we have for a sample of carbon stars. More precisely, we are presenting the mass loss rates, gas mass loss rates, and dust-gas ratio that we obtained from a relative transfer modeling of the dust and of the CO line emission. And here I'm showing 2 sets of plots. The top one showing the gas mass loss rates as a function of the expansion velocity and the period, showing the difference between the semi-regulars and the MIRAs. And on the bottom, I'm showing the comparison between the gas mass loss rate and the dust mass loss rate, and also the dust-to-gas ratio as a function of the gas mass loss rate for this sample of carbon stars. And if you are interested in the project or on these results, please visit my poster, stand number 1. Thank you.
Thank you so much. Mats André, if you have, if you have more than 1 slide, just tell me and I will move it.
Thank you. So I'm Mats André, Swedish Institute of Space Physics. I will be your friendly space scientist. So it's a long title with something about ionization, but the real question is, what about the magnetic field? So there are wind mechanisms for AGB stars, often pulsations and radiation pressure on dust will work. For red supergiants, maybe not so much. So could magnetic field and plasma be important? Well, I still don't know what I'm investigating. So to do this, you need charged particles. So what we have done is to take models, cobalt, you just heard about, and Darwin, and change this within a reasonable volume of parameter space. So what you see is degree of ionization as we change the temperature in a shock from a cobalt model. And the answer to all this is yes. In particular, in some regions, in shocks and so on, in some small regions, you can have a degree of ionization of 10 to the minus 4 up to tens of percent. So plasma effects could be possible. And this might be more similar to the Earth's ionosphere than you may think. If you want to know how, visit the poster. Thank you.
Thank you. Then we have Rajoshi. Are you online?
No, he's not.
No, okay. So Laurent will talk.
So my name is Laurent Charman. I'm presenting for Rajoshi Patagaya, who unfortunately couldn't make it. The poster is about AGB stars, of course. We have determined distances to about 15,000 thin shell AGB stars and divided them up in groups according to their location in the Milky Way. We have a local group, we have a group in the bulge, and a group in the disk that's in between. We have obtained their statistical luminosity distributions and derived that the local group has more short period semi-regular variables relative to the oxygen-rich Myras. And they also are less luminous than the Myras. They're more likely to have gone through their TDU events than the Myras, and these SRVs seem to be lacking in the bulge. If you want to know more about this, please come and talk to me, as Rajoshi is not here. But yeah, I'm very happy to answer all your questions.
Thank you so much. Next one is Elvire.
Oh, wow. I'm very sorry for this very small font. So I am talking not about AGB stars. So this is a poster on a red supergiant, NML SIG. It's a very extreme mass-losing red supergiant. So the difference to the AGB stars is that we're talking about several 10 to the 5 solar luminosities and mass loss rates of several 10 to the minus 4 solar masses per year. So we're a bit more extreme here, and with an initial mass that has been estimated to 25. So the behavior is also expected to be somewhat different, but the way we observe them is very similar to what we do for the AGB stars. So here, this poster is presenting some NOEMA data, so not ALMA interferometry, but NOEMA at about 230 gigahertz, so CO 2 to 1, and about 70 other lines we observed, I think. But the two plots that you're seeing here, the top one shows the continuum, where you see the star with a whole lot of dust around it, and then another clump that is at about 1,000 AU offset from this star. So we have in total about several 10 to the minus 3 solar masses in dust here, and we have some estimates on temperatures as well. We have then also correlated this with our molecular lines and seen that there's a lot of substructure, both on small scales and large scales. But I would suggest that you have a look at the poster, come talk to me, and maybe have a look at the paper as well. Thank you.
Thank you so much. Next is Mats.
Hi everyone, my name is Mats Esselders. My poster is on orbital evolution of AGB binary systems. So what I will present is how do orbital systems, orbital configurations of a companion around an evolving AGB star change throughout time? So how does the semi-major axis and the eccentricity change? And this can be computed by taking a look at how does the tide of these stars change the orbital configuration, as well as how do the winds change this orbital configuration. And both of these phenomena I have worked in detail on and can be found on my poster. And when you compute these things and you have a stellar evolution model, you can follow these processes throughout time and give you a semi-major axis throughout time for a companion, as well as you can see on the image. So that's what I'll present. And if you go to the next slide, this goes in combination with an observation of the AGB star Paiwan group, where in 2019 and 2023, we took ALMA observations. And using the combination of these two ALMA observations, where we see not only the AGB star, but also a secondary blob, if we assume or take the locations of these two components together with Gaia and Hipparcos observations, we can actually see that this is a secondary companion, a Keplerian orbit. We follow a secondary companion, which is surprisingly circular. And this brings us back to the orbital evolution. If we see that this is already circular, does this mean that it starts circular or has eccentricity? So you can compute the change in eccentricity. Turns out that it has to start circular, which is not really expected, so there's some tension. But for this, I will refer you further to my poster on poster stand 5. So if you're interested, please come talk to me there.
Thank you. Next is Heinz.
Hello, I'm Heinz from Universidad Andrés Bello, and this is one of the projects in which I'm involved that consists into continue work began by Momani et al. In 2012, where he proved that using mid-infrared data to create a CMD and combine it with a theoretical model that doesn't consider dusty mass loss, we can find a luminosity break where the observational data separates from the theoretical model. Next slide, please. We want to continue this work using 8 globular clusters with different metallicities in a range within the -2 and 0.5 dex to find if there is a correlation of mass loss with metallicity. So the stage in which we are now is to reproduce the work done by Momani, and looking at the plots, it seems that we managed to accomplish that. So the next step is to begin the photometry in the other clusters.
Thank you. Next is Tom. Oh yeah.
My number 8 or 7? Doesn't matter. Hi, hello, I'm Tom from the Royal Observatory of Belgium. My poster presents the work I've done on SED fitting of AGB stars with JWST photometric data in 2 extremely metal poor nearby galaxies, namely Sextans A and Zwicky 18, which have been mentioned previously today. So these SEDs were constructed with NIRCam and MIRI data, and I SED fitted above more than 100 stars for both of these galaxies with a radius transfer code MOV dusty to determine their mass loss rates. If you're interested in SEDs, please come visit poster number 8.
Thank you. Next is Liz.
So hi everyone, I'm Liz Humphries from ESO. I think it's widely known that ESO is now looking for its next big facility after the ELT. This is a process known as expanding horizons, and you can see that at the moment we're in the preparatory phase. ESO has asked for the next big science questions that should be answered in the 2040s. It will then ask the next big facility to answer these questions, and the process will complete in 2028. Next slide, please. So over 400 people have now got together to work on a proposal for expanding horizons to make a massive, a really game changer upgrade to ALMA. One of the things would be to increase the line sensitivity of ALMA potentially by a factor of 5 to 10, which depending on the diameter, of course, could add in around 100 dishes to ALMA, meaning we'd need a completely new operations model. At the same time, there might be a massive increase in the angular resolution. Obviously, this is also a game changer for evolved stars. So if you'd like to know more, if you'd like to get involved, please come to poster number 9.
Thank you. Next one, Susanne.
Thank you, Susanne Höfner from Uppsala. Yeah, I'm one of the dinosaurs from the 5 meetings, but for those of you who have not been around that long, Darwin models, if you don't know about Darwin models, so there's a quick summary. Again, sorry about the font. I had no idea how big the screen would be. So what we're doing here is spherical radiation hydrodynamics models of atmospheres and winds, time-dependent models. And so we have the shocks in, we have the pulsation in, we have grain growth and evaporation in. And the name of the game is to produce mass predictions for mass loss rates as a function of stellar parameters, to put it later on into evolution models, and of course to produce synthetic observations. And the poster is on 2 recent upgrades in the code. One is about the dust. So I recently put in SiC dust in addition to amorphous carbon, which drives the winds of carbon stars. It's a minor dust species, but it's important for the diagnostics. And the other thing is upgrade of gas opacities. There's new gas opacity data, which makes near-infrared colors agree better with observations. If you're wondering why we are still doing 1D models when we have 3D models, is I can do a grid of those in a week or 2, and it takes about 6 months to do 1 3D model with the wind. Thank you.
Thank you. Next one, Daniel.
Hi, I'm Daniel Jadlovský from ESO Garching, and my PhD is based in Czech Republic. And we worked on one of the largest samples of interferometric time series data for evolved stars, namely for Mira-type star RCAR and extreme red supergiant VX Sagittarius. We wanted to analyze the diameter variations and its relation to brightness over several pulsation cycles, also including for molecular layers. So for Arcarine, which is a Mira star, it works quite nicely. We get a phase shift of about half, which means that the diameter is the largest, is the smallest at the maximum brightness, roughly, although there is some discrepancy. And then the other layers, like atomic lines of titanium and scandium and water, are phase shifted by a few weeks from the continuum, which is related to the propagation of shocks and pulsations. However, at molecular layers, the variability becomes more irregular. However, then for the red supergiant, this is a completely different story because it shows an active phase and quiescent phases where the variability is very different. In the active phase, the variability is about 700 days and the brightness changes by several magnitudes, and then it's replaced by quiescent phase, which with shorter period. And this is also followed by diameter variations that also in the active phase, they have a longer period, and in the quiescent phase, they have shorter period. And also in the middle of data, as you can see in the last plot, by mid-2020, there was extreme mass loss event when the molecular layers got extremely expanded. And also in this time, there appeared a bracket gamma emission, which was likely this is due to passing of shocks, which is first such detection for red supergiant, for a single red supergiant, and also for star RCAR, we also saw bracket gamma emission appearing near maximum brightness, as is also known for Balmer and Paschen emission. And then we also compared 2 models. Next slide, please. So then we apply the same procedure to cobalt simulation over several pulsation cycles to see if we get the same kind of variability. And we selected one model which resembles my variability the most, and indeed we get relatively well phase-shifted variations for diameter and the atomic length. However, the phase shift is much longer than for the observations, so it doesn't occur exactly at minimum brightness, but later. And then also we computed interferometric observables and compared that to the observations. And the main difference, apart from the different phase shift, is also different strength of water molecular bands, which are much weaker in the models. And if you are more interested in this, please catch me later at the poster or elsewhere. Thank you.
Thank you. Next one is Franz.
I present a poster produced by Vlad Rastau, our PhD students. It's on HU Sagittarius, another object from the large program, this large program by Claudia. HU Sagittarius gained our interest when we saw this quite irregular eye-shaped dust emission in our Herschel-Pax data. And one of the reasons why we have this large program is, of course, to look if asymmetries in the outflows, deviations from spherical symmetry, special kind of outflows originate in regions close to the star. So, and these are preliminary data. They were just reduced a few weeks ago. But by now, we have the impression that this object does not show too much deviation from spherical symmetry close to the objects. Of course, the sizes are different in molecular region and continuum regions, but by now we've seen no clear indication why this object has these strange emission features far off the star. Thanks. Poster number 13.
Thank you. Next one is Elisa.
Hi, my name is Elisa Massa. I'm a PhD student at OEN in Madrid, and I will present my poster here, which is about our ALMA project. First of all, this project was motivated by the results we found in M192, a proprietary nebula, where we saw isotopic ratio changes for 1213C across the nebula, depending on the structure, and they are linked to the age of the structure with lower values for younger ejected material. So, if you go to the next slide. Okay. Here we have our ongoing work. This is our sample that we observed with ALMA in the last cycle. We chose 6 new planetary nebulae to observe and try to see whether this is a common thing in other nebulae. And well, if you want to know more about this, come see my poster at number 14. Thank you.
Thank you so much. And last one, Matthias.
Hi, my name is Matthias Merker from Chalmers University in Sweden. And what you see here is a detached shell in CO around a carbon star. And these detached shells, they get formed during thermal pulses. As we learned today, they're important for understanding nucleosynthesis in stars. And the exact properties of the shells, they depend on what happens in the star during the thermal pulse, so how luminosity and radius change, but also the mass loss mechanism, the dust formation, and the interaction with the pre-pulse wind. So we have these ALMA observations where we spatially resolve the shells, and we also get dynamical information on velocities and stuff like this. And if you want to hear more about those, check out my poster. And before you read the conclusions, please talk to me because I changed my mind on some things here. And now there's the reception, right?
Exactly. Thank you all.
Yes, but I forgot. I had the last minute announcement, but I forgot what it was. I don't remember. Maybe I will remember after a glass of wine. Thanks a lot to everyone for today. The reception is at the same place where we had the lunch. And we should leave the latest at 7. Better before, but yeah.
Lasciare lo zaino qua? Non credo.
No, I think it's better if you take your bag with you. And what I remember what I wanted to tell you, which is please remember to check on Slack because there are some questions for the speakers. And also, if you have some thoughts or something for the discussion, please send it to me. Okay, thank you.